see Mark Commode, and that's what he says all the time. So. Do you see it? Yeah, grand.
Okay, live stream starting. So we have like 1 minute.
And sit around. Can you promote her?
You know, start slowly.
I already did. She's a panelist.
Oh, of course. Sorry, thanks.
Hello.
Hey. Real quick, do you want to just check your slides work?
Sure. Okay.
Yeah, no, I'll wait a half a minute or two.
Let me start now and have fun. Take care. Thanks, Raj.
So, well, oh, did we lose Cedria?
I think so.
Yes. Hopefully you'll come back in and promote. But I'll slowly introduce people.
Joining the session. This is session 30. We'll rule 4 for make sure that everybody is clear. They want to join. We're going to wait a few seconds to allow everybody to join.
Yeah.
Hi, I don't know why I was it kind of like Zoom kicked me out of the room. I don't know why. But let me
try your screen share and then we'll kick in, start with Keith. Is anyone else hearing? Anyway.
So you see my screen, it's just white right now, right? And then I go to presentation mode. Everything is good?
Good, perfect. Okay, and I realized why I was hearing voices in the background is because I had the YouTube streaming. So that's a perfect start. So I'm delighted to introduce this session. We have 3 speakers, Keith Doling, Jifa Peef, and Seydinora Tikir.
That's good. Thank you.
Our first speaker is Keith. He's currently a postdoctoral fellow at l'Institut de l'Audition, or the Hearing Institute in Paris. It's a part of the Pasteur Institute. His work focuses on how the brain uses prediction to improve auditory perception, using a combination of computational models and neurophysiological recordings. He did his PhD in NYU in the psychology department. Oh, Keith.
Great. Okay. All right. Hello, everyone. Thanks so much for coming to listen to my talk. I'm excited to talk to you about my research on temporal expectations and probabilistic rhythms. The idea behind this was to start with a very simple task that's been done many times, which is to take a series of tones that are perfectly isochronous, and then have at the end an expectation place where you'll have either tone that's either earlier or later. And so you will have the subject say, oh, is this earlier or later? And so this task has been done many, many times. And one of the main theories that's come from it is that there's sort of an oscillator that may synchronize to these individual tones, and that you can use the phase as a means to predict when the next thing will come. Now, the issue here is that we know that speech, for example, is not so perfectly isochronous, right? We know that there's maybe a peak duration of about 5 hertz or 200 milliseconds, but there's a lot of variability there. And so how could an oscillator model deal with this kind of ambiguity? And so what we did was to just add a little bit of Gaussian jitter to each one of those expected tones, right? And so the question is, it's sort of in my as much Neuromatch Academy style as I can get, the questions that we're going to ask are, what do the listeners do? Why do they do it that way? And lastly, how do they implement the system? So let's start with what. And so the question of what really drives us home this question of where is actually the best expectation here. And that's because there's two ways that you can do this, which will each give you a different location at each moment in time, at each trial. So in one version is the sort of SOA version, where essentially what you do is you extract the durations between individual tones and sort of store that on like a number line. You put them all together and you take a mean. And after that, you just add that to the previous tone, and that gives you sort of a simple expectation. The other version, however, is to remember that there's this higher order structure here, and maybe it's your job not just to identify where each tone was, but actually where it should have been. And that will give you actually a different kind of estimation on a trial by trial basis. So we have this SOA and rhythm methods, and the question is, what do subjects actually do? So what we did is we just added a probe tone at the end that's either earlier or later, and we asked the subjects across 3 different experiments at 1.2 hertz, 2 hertz, and 4 hertz. We asked them, ours, was this early or late? And so we can define jitter based on either the SOA or rhythm methods. We can fit a logistic function and then use the slope as a measure of, well, which did they perform better at? And so in this case, this is an example of a subject that's better in the rhythm case. So now I'll show you the difference between these slopes on each one of these different experiments. And what you'll see is actually kind of a surprising effect that in the slowest case, above 0 means that you prefer SOA. In the slowest case, you prefer SOA. In the 2 hertz case, you're sort of agnostic. In the 4 hertz case, most subjects prefer the rhythm. And so this was a very surprising result for us. But we dug a bit deeper, and we found that this result is not just based on what rate you're at, but also on your overall performance. So now if you average those 2 slopes, which is what we see on the x-axis, you see that the subjects that perform better overall prefer this sort of SOA kind of effect, and the subjects that prefer the rhythm, that are doing worse overall prefer the rhythm. And this is a really significant dip below 0. It's not just like a regression to regression to 0. So this is the what effect. What we see is that depending on how well you do, you actually shift which kind of method you're best at. So the next question is why? And the answer is because it's optimal under certain sort of Bayesian assumptions, right? So the first assumption is that brains measure temporal intervals with some amount of noise. The second is that we should expect some expectations for each individual tone. So this example where I have 3 tones, I can expect the 4th one because I expect that intervals should be more or less the same. And lastly, that we should combine our expectations with our sensory input to generate some final estimation. And so if you build a very simple Bayesian model of this kind of situation, either as the SOA or as rhythm, you can see that actually the SOA Bayesian model looks very similar to what we saw in the human data. That when you have low precision or high noise, you actually rely more on the expectation of rhythmicity. And so the last question is, so how can we actually do this kind of thing? And so we decided to go back to this question of the oscillator and see, well, how far does it actually get us? And so what we did is we took a sort of Wilson-Cowan model of an oscillator, wired it to be at about 4 hertz, and the 4 hertz condition on this stimulus. We drive the excitatory inputs by this acoustic stimulus. It has a coupling value that allows us to change how much the input actually drives the excitatory system. And what we do is the oscillator sort of synchronizes to this input, and we can extract the phase either at the expected SOA location or the expected rhythm location. We can see how consistent is it at each sort of coupling value. What we find is that for low coupling parameters, you actually see higher consistency for the rhythm case, and in higher coupling values, we see higher consistency for the SOA case, as shown by these 2 examples here, suggesting a sort of similar kind of mechanism to what we've seen in the human data. And lastly, what we did was to not just take the expectation phase, but the phase at the final probe tone, right? So, and then you can use that phase as a means to predicting, how to have the oscillator do the task. Is it early or late? And again, we found a similar result that when you're sort of below a certain level of performance, you prefer the rhythm case, or the oscillator does. And when you're above, you prefer the SOA. And so this is, it's not a perfect model, but it shows a kind of example of what kind of models could actually do this kind of shifting in method depending on different kinds of levels of noise, suggesting that maybe we can use a neural oscillator as a kind of neural heuristic for a rhythmic prior. And so with that, I want to thank you for listening. I'm happy to take as much feedback and any ways to improve this as much as possible. And I want to thank, of course, my fellow researchers, Florencia Aseneo, Luke Arnau, and David Popel.
Thanks so much, Keith. That's really fascinating work. And spanning all. So just out of curiosity, on my own side, with your modeling, is it just simply that you've done excitatory and inhibitory, or are there more than two elements in that model? Have you included, like, it's inducing, like you have there the classic, so you're having it being driven by the stimuli. Is there anything else in that model? Is there anything more, other layers to it, or is it just?
It's really just these two
that
differential
with the
equations here. So
Yeah.
it just so it has a couple things. So one, it has a parameter for sort of outside input into the system for both sort of base level of inputs to the excitatory and inhibitory populations, its own sort of recurrent connections and cross connections, and then lastly, just this input into the excitatory system of the acoustic signal and our sort of gain function. So, I mean, the trick is in the parameters that you choose, right? And so you can make this model either an oscillator or not. So we've chosen these parameters to be specifically in a sort of Hop oscillator, and to have it be at around 4 hertz to match the time constant of the inputs. But other than that, it's just let it breathe.
Oh, it's fascinating. Like, so we have a couple of questions here. The first one, do you think these two strategies represent different neurological mechanisms for performing the task? As in, is it that it's integrating two sources, or a continuous? That's from John Cannon. Nice question.
Yeah, so that's a good question. I don't have an answer yet. So what this sort of shows is that one oscillator one mechanism can actually give you both types of behavior. So it could be that this is sort of almost enough on its own. I could also see a version of this where maybe the oscillator is only really doing the sort of rhythmic part. It actually only exists at a coupling parameter that's sort of low, and there must be some other kind of estimator that actually does the sort of duration actual estimation, and so there's some weighting between the two. So by the way, there's just to show you, it doesn't actually have to be this way. So we also sort of built a sort of ramping model where you just sort of measure each individual interval through some sort of like ramping with noise, and then you save the value at each new tone, right? And so then you can sort of take an average and have an expectation here, which shows you a clear SOA kind of effect. And it never actually chooses the rhythm model at any kind of level of noise. So maybe there's some sort of weighting between these two kind of things where instead, you know, you choose the timing based on the phase or something after the oscillator or something like that. I haven't quite figured that out, but it's an important next question.
Yeah, no, then that kind of got back to, like, I was wondering, because your model, as you say, is rhythm. In theory, you could have a second model that's doing something else, and then a third model that it all feeds into. You know, take a Bayes approach to it. But on a kind of technical level, Yao Arujo was wondering, how do you optimize parameters for the Wilson cone?
So we don't, is the answer.
Right.
So the only things so all of these parameters are basically chosen from like weakly connected neural networks, like the Zhikovic book, right? So there's so they're just chosen to be sort of at the Hop boundary. And then we just choose tau so that it should be at about 4 hertz. And that's based on lots of work in auditory research that suggests that 4 hertz is a good time, and it also matches well with the data. We actually haven't done this yet with the slower simulant. So another question is, does this work as well when you change the frequency, right? And how do you actually shift frequencies between different things? But so we just chose it at those kind of set parameters. And
there is there's work by Jeff Yao, who is some behavioral work looking at how auditory, processing time and frequency in the auditory system and how they can be messed up in different ways, and suggesting like they can be viewed as separate, but maybe around certain frequencies. So your 4 hertz is a bit of sweet frequency that the two, like there's an overlap, and and that's why there, biologically that I'm sure there's some natural statistics that suggest there are sweet frequencies that people prefer using one or the other, or like that's more naturalistic. But yeah, really, really lovely work. And as as Felipe said, lovely to see the Neuromatch Academies thinking coming in. I feel sometimes that I wonder if we've all drank a Kool-Aid. Anyway, so we'll move on to our next speaker, but do keep putting in questions if you have more questions for Keith. And if there's time at the end, we can have a discussion. So our next speaker is Sophia. Sophia is doing her PhD in the University of Technology and Economics in Budapest in Hungary. She did like me, Go Maths. She did her undergraduate in maths, and she's interested in application of computational models. So yeah, Sophia, over to you.
Thank you for this kind introduction, and welcome everyone. So my presentation is somewhat connected to this previous one, as our research follows the Bayesian framework. This theory states that during perception, the brain actually infers from sensory evidence. This is the so-called likelihood, and also from its priors, which are influenced by previous experiences. It can change from person to person and situation to situation with how much weight the prior and the likelihood will be taken into account with calculating this posterior, which is basically the percept. Previous studies showed that during an associative learning paradigm where, for example, certain sounds are mostly followed by certain tilting direction, people mostly decide based on these learned priors, even if the likelihood of the tilting is very low, as there's no sensory evidence of any direction. Like this. In our study, we were curious what would happen if they had a chance to learn visual cue target contingencies too. In that case, in ambiguity, cues from the acoustic or the visual domain would have greater influence on the percept. Secondly, we wanted to make sure that any differences found between participants are momentary. So we measured the values 1 week test retest reliability. For achieving this, we asked participants to make several decisions of dot pairs turning directions, which they indicated by button presses. Every turning was preceded by a multimodal cue, which consisted of a dot moving up or down and a higher or lower sound. Most of the time, we showed cue target pairs from which they could form associations. Sometimes we showed cue target pairs which contradicted this rule. Furthermore, sometimes the target was ambiguous. In half of these cases, these were preceded by the known cues, so we could measure how much the decisions were affected by the associative learning. And in the other half, these were preceded by cues where the parts from the acoustic and the visual domain were associated with different directions. Here, the effect of modality could be measured. This underlying rule of motion directions could change after 40 trials. So let's see some of our most important results. We replicated results from previous studies showing the effect of the associative learning. On this figure, you can see the difference between the median reaction times of each participant in seconds. Most of them answer slower to the less predictable motion, which could mean that the calculation of the posterior took longer when the expectation differed from the perception compared to when they were the same. We also examined aggregated indicators of decisions. Here you can see that from all of those trials where the known congruent cues were followed by ambiguous target, what percentage did participants decide on the associated direction? As a group, they scored above chance level, but there's high variability, meaning they had differently weighted priors or maybe some formed none. But we were interested not only in associations in general, but also in the differential effect of the cues modality. On this figure, you can see that from all of those trials, where the slightly confusing incongruent cues were followed by ambiguous target, what percentage did participants decide on the direction associated with the auditory cue? There's high variability in this data. Many performed close to chance level, but as a group, they scored above it because some seem to choose, most of the time, the direction associated to the tone. We could say they took the acoustic priors with bigger weight into account. What one could see from the mostly parallel lines beforehand, we could also measure by test-retest R values. All of the above mentioned indicators were temporally stable. On these figures, we plotted results from the first and the second session, and the correlations were just as good as one would expect from a questionnaire, which can provide a basis for further research. To wrap this up, we found large and stable differences in behavior due to our experimental manipulation, replicating previous results, and as a novelty, finding a bias towards the acoustic cues by forming associations. You can read more about our research in an already published conference abstract, which contains some more preliminary results. And I also put on this slide the article on which our experiment was mostly built upon. I'd like to point out that as this experiment was mostly exploratory, the potential underlying mechanisms are still up to discussion. Future studies might help understanding them. And thank you for all your attention. I'd love to hear your thoughts, questions, opinions.
Thanks so much, Sophia. So is the goal, like, replication is so important, and especially with something that, as you said, has high across participant variability, but also the nice within participant replication, it seems to be quite consistent. So was it every week they come back to do that? And what would be like, so you've replicated, and I see that you're thinking schizotypal, things like this. Is there a model that you think that this kind of multisensory integration is important for, or how do you think, like, maybe, and it's a very general question, but why maybe multisensory in this case?
Why multisensor? Well, actually, everyone talks about perception and the levels of it, and when you do this task, this associative learning task, you have to associate a tone to a visual motion. But that's what they did in previous studies a lot of times. And this actually expects the participants to use their cross-modality. And it's a higher level association, I can't talk, I'm sorry, association already. So it was very interesting to see if they have a chance to do this on a lower level, what would they do?
Yeah, and so part of your plans were computational modeling of it. What kind of models were you thinking for this to drive this? Like, you don't have to give specifics, of course, but kind of interested in how the multisensory changes and thinking how it affects the prior, or how, for example, like, so, you know, as they learn, it'll sharpen, you know, a bias towards one, in this case, the auditory or the other. What were you thinking of that in that?
So, computational modeling. The reason I put this study on, this Weinhammer study, is because our paradigm really is mostly like this one. We did some changes, but it's mostly like that. And they had this nice computational approach. They have this great model, and they didn't use this cross modality. So we planned to use that model to work on that and finally I use this for the auditory cues or use this for the visual cues and see which one describes participants more. Maybe there's a great difference between those two. So we can include this cross modality in that model, and it's a 3-level hierarchical Gaussian model, actually.
Yeah, oh, that makes sense. Well, thanks so much. It's great to see reproductions, and then it's like with my own students, it's great at the very beginning to reproduce, because then you know you're on a firm footing, as opposed to assume, and then you don't know why the model didn't work. So it's a great place to start. So we'll move on to our next speaker, who is Sitanur Tikir. Now, I probably declaration. She is in a lab that I did one of my postdocs in. Sophie Malaham was a postdoctoral supervisor of mine. She's in the cognitive physiology lab with Dr. Sophie Malaham at the Albert Einstein College of Medicine in New York. And she studies predictive processing in autism using EEG behavior, machine learning, and computational modeling. And actually, just on an overarching thing is that it's lovely that everyone is starting with the behavior to drive the models, as opposed to having a model that drives the thing. So that's a really lovely consistency. Now, hopefully I haven't undermined, and yours is all about modeling. So, see down. Yeah.
Thank you, John, for this introduction. I'll share my screen. All right, so you see my screen, right?
Yes.
Good. Okay, so thanks everyone for being here and listening. Today I'm going to talk about my research in autism. And so my research is about predictive processing, and our brain is actively producing predictions about upcoming input all the time, rather than passively receiving, right? Probably by this time you generated some predictions about the Zoom. Once you click on a Zoom link, you may expect a pop-up, depending on your experience. And then maybe when you're having breakfast, if you make a toss, you might just put the lever down, and in the meanwhile, expect to hear that click sound or lever staying while not actively thinking about it. So it's happening all the time. And these are emphasized recently by this hierarchical predictive processing framework, where top-down connections carry predictions and bottom-up connections convey prediction errors. So we not only make predictions, but we also adjust the certainty in our predictions, right? For example, when you push the lever down, if the toaster is problematic and you don't know if it's gonna stay click or stay down or not, and it could be a little changing from time to time, and how certainly you're expecting this outcome will depend on your experiences, right? If your experiences are all green, meaning that it always stayed down in the past, then you would expect very low error rate, and you can expect this certainly. And then further, if you get more information from environment and then sometimes it didn't stay down, you can kind of increase that error rate in your mind, uncertainty. So over time, we keep updating the certainty in our predictions, right? And it's very important that we can flexibly update the uncertainty in our mind. So it's been, predictive processing has been a recently popular topic in autism. And this has been influenced by one of the major hallmarks of autism, which is insistence on sameness or intolerance to changes. And so possibly this could be related to abnormal predictive processing. And that's why people with autism resisting to changes in the environment. So I hypothesize that people with autism are unable to flexibly adjust that level of certainty in their predictions based on the statistics in the environment. Today I'm going to show you two experiments that I did to test this. So in the first experiment, we have a sequential pattern test. There's a shape one at a time on the screen. And then the shape changes about every second. And the sequence of this shape can create a pattern. This is one pattern, up, right, down facing arrows, and people are supposed to click after that. And another pattern here. And people are told to click after that before the experiment. And I also do a mobile training 1 day prior to the experiment. And so this is a sample sequence of stimuli. If the shape is just circle or unrelated, they're not supposed to do anything, but after the target, they click. And after the cue, if it's not followed by the target, they're not supposed to click. They're supposed to withhold their response. And over the time, throughout the experiment, I modulate this rate of pattern completion versus incompletion at 4 different levels. As you see here, 4 different pattern completion rates, 4 different experimental conditions. So this is a sample timeline of the experiment. For example, here we start with 100% expectancy. And then we lower this, and then it increases and decreases. And we introduce about 11 times of switching to this experimental design. And throughout this time, we also measure the response time, EEG, using high density electrophysiology. So there are two evoke response potentials that I'm focusing on. First, it's the P3 response, which it changes in amplitude depending on the probability, and also the CNV response. So P3 happens upon targets, whereas CNV is an anticipatory response that occurs while the person is expecting an upcoming input. And when I see these different conditions in neurotypical group, I see that 4 levels modulated, or this is what we expected. The P3 amplitude is modulated depending on the probability condition. In autism, this was different. Although condition 1 was differentiated from others, the differentiation between condition 2, 3, and 4 was much less. And this has also correlated with some clinical scores. As individuals had higher repetitive behavior scores, it decreased. So I also did an experiment, mismatch probability task, where people are responding to, where people are not responding to any targets. They're giving by the standard auditory inputs, and then I introduced some deviant tones. It could be a duration deviant, meaning that the tone is coming earlier than they expect, and it could be a pitch deviant, meaning that the deviant tone occurs at a different frequency. And I also modulated that at 3 different probability conditions. So in mismatch negativity task, we know that there's a negative potential to deviance happening about 150 milliseconds. And if you subtract their standard response and deviant response, you would expect to have a positive peak at around 150 milliseconds. And the amplitude is smaller in the higher deviant conditions. So when I see the results, I see that in neurotypical, similar to the previous experiment, this has modulated, the amplitude of mismatch negativity is modulated by different conditions. And this was also modulated in the autism group. And this was the case for both types of deviance. So these 2 experiments makes us conclude that maybe the specific problem with predictive processing in autism is not registering the statistics, because people performed well in the MMN task as well, but maybe it's about applying the statistics to flexibly adjust the certainty, because the task performance was bad in the first experiment. And this is what we think. I wanted to ask also what machines think, leading me to do some machine learning classification work in collaboration with the laboratory of Rubin Joan Jolly and 2 students, Jonathan and Dylan from his lab, 2 postdocs. So I trained a classifier to predict autism based on EEG signal first. And I was hypothesizing that the best classification success will be achieved when the target trials for all conditions are given as input. And this is the results. In the y-axis, we see the success rate. And I did this differently for each type of trial. And the target trial is the trial that we focus on, that we base our hypothesis on. So it had the highest success rate. And when I repeated the experiment with different individual conditions, so condition 1 only, 2 only, versus all conditions, I see that for the target trial, the success rate increases significantly when I input all conditions, meaning that the classifier are much better when we input all different conditions. So this also is in support of our hypothesis for inflexible predictive processing. And I also did another experiment where I decoded the conditions rather than the diagnosis groups. And I tested for each subject how well subjects can differentiate different conditions. I trained the classifiers for that, and then calculated a score for each subject. And on the y-axis, you see this condition decoding score, and on the x-axis, you see this repetitive behavior score, which is also an inflexibility score. we see some negative correlation, although it's not very strong, which could be in support of our hypothesis as well. So really, from these two experiments and the machine learning classification, I think that the specific problem with predictive processing in autism is not in registering the statistics, but it's in applying the statistics flexibly to flexibly adjust the certainty in the predictions. I'd like to thank my advisor, Sophie Mulholm, and all my collaborators and lab members, and thanks to NeuroMatch community and everyone for listening.
Thanks so much. So I was curious, in the first task, was there a, did you record how fast they were responding between the two groups?
Yeah.
And was there a difference there? Yeah,
so I actually can show the results for that too. I recorded this and we see a difference in that. All subjects, so by the way, all subjects responded well and the performance was good. And so the mean reaction time for autism group, which is shown in red, for condition 1, 3, and 4 was much more stable, and it's at 240 milliseconds. But for condition 4, it was a little bit higher, but in neurotypical, it was more flexible across different sub-conditions. So this was also in support of our hypothesis.
Oh, there's a hand raised.
Yeah.
Actually, just on a follow-up on that, while I figure out who's trying to ask questions, there is an issue with the P3. You could response lock it, and then the accumulation of the P3 could be consistent between the three groups if you, instead of stimulus locking, response locking. And that might be able to tease apart the different.
That's a great idea. I know that in one of the article by, I think, Simon Kelly, and I forgot.
Yeah, Simon Kelly's work and Redmond's work, and
yeah,
would be a good place to start looking at that, because it's to tease it apart.
Yeah, I haven't done that yet. Thanks for the idea. I think that would be interesting. Yeah.
But I think that will actually address, because what you see there is the flatness is probably due to response variability, and it might be something earlier in the feeding of the automatic to the decision, because the decisions are correct. You're saying, like, the accuracy is
exactly. So the decisions, the performance is about like 90%. So even the lowest performing subject responded to majority of, like, about 90% of trials correctly. And so this is less of an issue in this case, but still, I think it will be interesting to test that.
Yeah, no, but it's but I think it's important. It'd be important to tease those two apart.
Yeah,
as you say, the end. I'm delighted, but also surprised, because you know, an auditory task like the mismatch, like from work by Alice Brandwein from the lab and all. I've always had the suspicion that auditory is the one that is to be mined the most, probably for autism, and visual things are less, they're more subtle and more diffuse, the difference between neurotypicals and children with autism. But that'd be mine.
Yeah, that's an interesting question too. I would expect that if there is, so, you know, this insistence on sameness in autism, or like different autism phenotypes, happen in different modalities, right? Sensory precision, it's all in visual, sensory domain, and auditory domain. So I would think that if, like, predictive processing is abnormal, it's more like a general central level that affects all modalities. But
yeah. Oh, yeah. If it was decision making, but auditory is different. Like your co-author, Michael, Mick's work, you know, showing that, like, the auditory processing, speech and so forth, it's quite different, and you know, it could be quite a different development to it, because it's so vital, in my mind. But that's just a suspicion more than anything else. I've not found, like, I personally have done always say that things look the same. So we have a question. from Lu Wang. Do you have, have you published any of this yet? And is the machine learning code open source code?
No, I'll share it. Once this is published, I'll make it open source. And even now, if anyone is interested, you can feel free to email me or text me and I'll be able to share it. But I'm a big supporter of the open source like science environments, and I like neural nets, so I'll be very happy to share.
Like as someone who loves EEG, EEG is very, very noisy. So to get any kind of result from machine learning with such a noisy signal is hard. I found, and especially with a non-heterogeneous population like autism. But that's why I was, as I was saying, linking all the 3 talks, is that a nice, interesting behavioral task was what brings to light differences, and then modeling and so forth. But if you don't have maybe an interesting task or a task that challenges, I think about all 3 talks today have shown that a solid task is what matters more than anything else. And then you can drive the understanding of different processes. No, I like that. It's a lot of work to record from, as I know from my time, to do these recordings. So that's.
Yeah, by the way, just as a follow-up to Lou's question, so I the techniques isn't in an open source code, so I didn't take it from any publication. We did it with Jonathan Macher, who's one of my collaborators, so it's not online yet. Just I saw that there was a second question, so yeah.
So,
right.
Great. Thank you. So that brings this session to a close, actually, on time, which is great. Slightly a bit early. Grand. If there are any other questions, do contact the speakers. I've dropped in the Twitter's feed for 2 speakers, and I'm sure that Sophia, you could find her online as well if you have any questions. No, but we will, of course, look forward to this work coming out, as always. That's a great thing about these kind of talks, is people presenting stuff that's on the way there, which I love, as opposed to, well, my talk later on is it's done, so I'm not going to listen to any comments or complaints. It's published, leave me alone. So
I can ask a question for Keith, by the way, if we have time. So, well, what do you think about like your results? How is it in different modalities? Do you think that they extend to different modalities as well?
Oh, such a good question. I have no idea. We haven't done a sort of visual version of a rhythm task. I know that people are generally less sensitive to temporal changes like this, and so it could be, because if there's more, let's say temporal noise or something in the visual domain, that you have more of a reliance on the expectation. So maybe that dip is actually like longer. But it's pure speculation. I haven't thought at all about.
I did a series of studies back in the day in Einstein where we did looked at duration discrimination in the auditory system and the somatosensory system. We predicted that should feed into each other. It did not. They were separate. They were within modality processing, which we were surprised by. We had intracranial recordings and scalp recordings, but frequency. Now that did communicate between somatosensory and auditory. And so, like, as you're saying, I believe it should be tuned by what the sensory system is tuned for. It doesn't make sense that they should all do the equal thing. It should be, a task that works really well for the auditory system will not work well for the visual system. I'd say the frequencies won't be nice for it, but also for somatosensory, somatosensory is the closest. And once again, the work by Jeff Yao was a lovely behavioral version of what we did as well, looking at those subtle interactions of task and modality, sensory modality, sensory system, and how there's a strong interaction between. There can be very strong, but also there can be very weak, because it's environmentally driven. And that's why I was saying with the different frequency ranges, where the different SOAs, it might also be that it's less tuned for that, and therefore that's why you weight it less, because it's less in the environment. But if you have something that's close to the environment, that's when you start choosing one or the other, or like, you know, doing these kind of weighting. But it's very complicated, and you'd have to appreciate the natural statistics of the environment for it.
So you mean that when you said that there are different systems, was it a multisensory task, or is it that the effects are just different across different? Okay.
I was looking at them individually at the different brain areas, and then at the combined version of it. And what we saw was linear combination for duration, and also that there were, we were able to find the locus. While with the frequency, we saw a non-linear combination, which would suggest that there is some kind of strong amount, but duration, which we thought, and we wrote it back in the day as, hey, I was really surprised. I thought this was going to work out great, but it worked out the other way, which was great as well. And
yeah,
it was
exactly.
nice to have that reverse. So
nice design.
You fall ass backwards into some things. So I would like to thank everyone for their lovely talks and very interesting talks. I would also like to thank Felipe in the background, who's been making this run smoothly. And thanks everyone for coming along. So thank you.
Thank you guys.
Thanks everyone.
Thank you. Bye.
Time, but please someone make a screenshot of me and my teacher.
You can try.
Okay, I hope someone got that. Oh, it's also really warm in here. Good morning, everyone. Thank you so much for joining. I know it's not morning everywhere in the world, so I apologize for that. But here it's 9 a.m. and I'm really excited to be joined here this morning by Sotirios and Fotios. They are both in a European time zone. So let me just quickly do the math. It must be, well, normally I'd say it's 3 p.m. where they are, but they just moved already to winter time. So I think now it's 2 p.m. Yes, okay, thank you. So my parents are in the same time zone. I am originally from the Netherlands. So I typically know that quite well, but this time shift is always a little bit confusing. It's going to be...
So when you send your emails, I thought, okay, this would be really funny if it's in the USA.
Yeah, no, that's true. I am. So today we're gonna start our talk with our session with Sotirios, but I wanted to explain a little bit about what's going on in this session. So unfortunately, we had a cancellation of our second speaker, which means that we are kind of, we have to deal with a sort of dilemma here of what we're going to do. Because the last thing I want is that people will join this session to look at Fotios' work, who's going to be presenting third, and then they might miss it because we shifted it to an earlier time slot. On the other hand, if we lose people in this session because there's 15 minutes of nothing, then that would of course also be very unfortunate. So we're gonna put up a poll. I think Saeed is joining me at the back end, and he said, well, we can just do a poll. So maybe that's what we'll do. But of course, there won't probe people that are actually not in here right now. So I think what's going to happen is that we're going to start with Sotirios. Then we're going to directly go to Fotios' talk. And people that have missed Fotios' talk can just rewatch it on the YouTube, where we're also broadcasting, etc. I think that is probably our best option. And at the end of the session, when we still have time left, we can maybe get some more questions and have the speakers answer more questions if there's a need for that. Otherwise, we can tell each other spooky Halloween stories. So having said all that, I think it's time to really start with the session. I'm really excited to announce Sotirios Panagiotou, who uses he, him pronouns, and he's currently a PhD at the Erasmus University Medical Center in Rotterdam in the Netherlands, and his supervisor is Chris de Zeeuw. His research includes neural modeling and simulation and functional ultrasound analysis, and he's especially interested in the interaction between these things through neurovascular coupling. He is unfortunately not on Twitter yet, so maybe you can all encourage him to join the Twitterverse. When you're ready, Sotirios, take it away, please. Thank you so much.
All right, now let's start. Let's go. All right, so are you looking at the slide? Is everything all right? There's nothing obscuring the screen, right? Great. Okay, wrong button, sorry. Okay, it's everything fine, right? All right, so to begin with, sorry, I'm Sotiris Panagiotou, and I'll talk to you about the work of our laboratories, the National Technical University of Athens Microprocessors Lab, and also the Neurocomputing Lab of Erasmus Medical Center, which is where I'm working now, on neural simulation. So we made a simulator of neural networks, not the artificial ones, the spiky ones, the biological ones, which is supports mostly any kind of model. And it does this while being very usable and being extremely faster than the mainstream simulator. So everyone here is working indirectly or directly in larger or smaller scales with networks of neurons. So in general, we want to try out how the neurons will react to scenarios, and this thing we do this through simulation. So we might try an experiment before running on paper, let's say, based on our model. Or we might propose new features to a model that explain better effects we've seen experimentally. So we need to verify our model against existing experimental datasets with a virtual experiment. Then we can try these things in vitro, but these experiments are much more expensive, time-consuming, difficult. So we need to do anything in silico if we can save some time in the wet lab. But then, especially because we use especially large models, so we can get more subtle and more intelligent effects of neural tissue, we have to pass the calculations to a computer. There are extremely many. So in practice, we have to solve the equations. We have lots of equations. We really stress the computer. And these nice pictures, I put them in because they're nice, but they explain the large scale of the model, like in coupling, where the color might mean something like delay or so, or strength of connectivity. They will have one isolated neuron, and then we have the specific biology, the mechanisms work inside the neuron. And this is the domain that the simulator has to work with to replicate one neuron and even a whole part of the brain. So that's to imagine the scale. So what do we want from a neural simulator? We wanted to do the calculations efficiently so we can make the models fit in our machines and provide results in a reasonable time. And this is the computer is the limit in how detailed and how crazy models we can try out. But then again, one model is not enough for everyone. Cells are hardly the same across the brain. So we need to allow everybody's formulations to run on the simulator. And we have to keep in mind that new formulas will be added all the time. So we need to support everything and anticipate everything in the equations. Novel models have different equations because they're novel. But then again, that's a recurring problem in silico neuroscience. We have to allow researchers to pass their models on the computer without them needing to become computer scientists themselves. This is a major problem, and it's increasingly important as computer power grows. We can't harness computer power effectively if just setting up the model on the simulator takes a couple of years as a specific project in itself. So we designed a simulator to handle this. And the specific features are, we can run all types of models in the new NeuroML specification, whether they're biological, whether they're artificial cells like Izikevich cells or integrated fire cells that Fotis might know about, or even mixed networks. We do them all because every single team has their own model with their own complications. Either you support everything or you support nobody's stuff fully. Then, compared to the mainstream simulator, Neuron, our models run tens of times. Our simulator runs the same models tens of times or even hundreds or more of times faster than Neuron. And a simulator can also run on supercomputer clusters. So this is the case, for example, if we want to use whole cubic millimeters of neural tissue, we can't fit it on one machine. We have to use a cluster of computers to do this. And all this stuff is done automatically. You don't have to learn a specific specialized programming language of the simulator and fight against its limitations. You can use whatever tool to create the models in the declarative NeurML standard, and then you can run the model on one processor or all processors of your PC on a supercomputer. Everything is automatic. So these are more specific the features of the neural network. This is in case you can get any terminology you're aware about. So, for example, we might have adaptive exponential neurons, Zkiewicz neurons, integer phi, which is most simple. You can have biophysically detailed with ion channels, with ion mechanisms, and so on. You can have mixed networks. In the case you can't model all the neurons biophysically, or you don't have data. So if you have Purkinje cells, which are very complicated and very simple, you can replace them with the fire, and so on. You may have spike-based chemical synapses with one-way transmission of neurotransmitters in whatever formula you like, basically. These are the most common ones. You also can have graded synapses, which is when, for example, a neuron leaks electrons or ions to another neurons directly, and this is how they manage to synchronize the firing. And there are very many important effects that are based on what the neuron does when it's not spiking yet. It has oscillations which don't lead to spikes, but they're important. They prime the networks, etc., etc. And you can describe all the dynamics in whatever equation you like, based on ordinary differential equations. But you can have switching behaviors, you can have random numbers, random effects, and so on. So then, once more, usability is through automation. No neuroscience has a completely fully automated setup, but if the parts of the pipeline, like the simulator, are themselves automatic, it saves a lot of time. So with a declarative standard, selecting the simulator you're going to use, if you're going to use spiking, simplified networks, more biological networks, it won't marry the user to specific tools. You can use any tooling that's with the standard. You don't lock in yourself to what the specific simulator supports in terms of packages and data formats, etc. So, for example, do you want to define a neural network with your own laws for morphology and synaptic projection? You can implement it in whatever environment you like, export it on the declarative standard, and load wherever it's most appropriate for the case. Also, our simulator also validates the model, so you won't have strange effects that's because of the model is defined. The program detects it and explains, for example, if you've mistyped something, it will explain what the problem is and why it's wrong. And you can run all the stuff on parallel computing. I repeat it once more, because currently it was a major problem with, for example, Neuron. You had to write your own code to make it run parallel. You had to manage your own communication between computers. It was terrible. And software engineering for this thing took more time than running the simulations. So also, we want people to use it easily. So we have made our own Python package that helps you take the results of the simulation within your own scripts. We also use Docker. So you have a specific reproducible setup, and you don't have to spend time to set up the simulator or learn about Linux and stuff. It's properly installed every time. And we combine these things on Binder, which is an infrastructure. So you can run your own Python notebooks and deploy them in terms of, for example, a class for an experiment or for your own personal use. And and the rest of the list most with the details. So let's see some specific cases. For example, say what happens with performance runs. Initially, you as a modeler try to find equations that reproduce the behavior of the neuron you're modeling at the basic stage. You just need to see that it has oscillations, burst-based firing, and so on. Then you fine-tune the parameters later, but you have to define your own equations. So this is an interactive process from the formulas you're proposing to the results of the explorer of the simulation and back again. So in this case, one or just a few simulations, they have to run as quick as possible so you can change your equations. So you can find one instance that replicates the results. So in this case, you have a model, possibly a very large model. And to make it run as fast as possible, you want to use all the cores of your computer to spread to share the computational effort to make one simulator run as fast as possible. And of course, if it's extremely huge, you just have to spread the effort to between different machines. So this is the opposing case. After settling on your equations, you may need to prove the model is general, so that the parameters didn't work by chance. To do this, you might use, for example, sensitivity analysis to see this was not just a fluctuation. There's a stable region that reproduces the same spiking results. So in this case, you want to run an offline batch of thousands of simulations to get a full card of combinations of parameters and the behavior of neuron. You may have found these graphs. Like 2D, for example, they have different colors for different states of neuron, resting or spiking or bursting. But then again, you do need your simulator to be able to run on multiple cores. For example, if you have a huge network, it won't fit 8 times over in your computer's memory because it's huge. So if you want to use all your 8 processors, you'd be better off running one simulator on 8 processors because otherwise it won't fit in memory. And also processors are usually not as fast when they run through a lot of memory for the model. So often it happens that simulation on 8 cores, for example, it runs faster than 8 separate simulations on specific cores. Okay, that's a lot of time. Sorry. So then again, these are the specific models. You can ask me more about this later, sorry. And these are specific numbers. So we can see we have this is a simplified model. We have a great speed up, and then we have an even greater speed up and extreme speed up for complicated neurons. So these are the points. I think I explained them in length. And I'd like to use this link. Could you please start a copy it and publish it on the chat? You can also use this email. I'll post it for you. And so this concludes my presentation. So then I'll answer any questions, and we have extra time. If you want me to expand on these topics. Thank you.
Thank you so much, Sotirios. So our own Dan Goodman put a couple of questions in the Q&A box. I cannot have you answer them all because then we will get some time conflicts, but I will ask them. So he's asking whether you've considered adding GPU support.
Sorry. So about GPU support, this is certainly the next part of our development. But first of all, we have to have CPU support, so we can have a proof of concept to see how fast it goes, and then we can support the GPU. But this is indeed one of the next steps.
Okay, great. He was also asking how the performance is compared to Brian and Nest.
Yeah. So the thing is that Brian and Nest have different programming languages. So it's not trivial to make. If you have to program the same model again and again, you have problems. So Brian and Nest, they run on UML, but the difference is they focus on spiking neurons or simplified neurons. Brian just now has some morphological extensions, but they're not enough for general biological neural networks. We're more targeting neuron. And in this case, its performance is comparable to neuron, probably rather slower for simplified networks compared to Nest. But the thing is, it supports all sorts of models, so it's more like neuron in this case.
Okay. sorry.
For the third question, I think it's about specifying inputs into the model, like stimuli, whether the video or not. And in fact, UML doesn't have feature for that. That's the second thing we want to focus, along with GPU support, because that's a major problem for everyone who has a setup in MATLAB, for example. They have their own videos, etc. They want to port the model, and NeuroML needs to support this. So we might have some experimental support, and then pressure the NeuroML committee to add it or negotiate how it will fit in.
Okay, thank you so much. That was great. Yeah, Dan is still around in the chat, so if you want to talk to him shortly, then by all means, go ahead. Just for people that have joined us, Said is telling me that, so this is a little bit confusing. We had a speaker now scheduled who is called Said, and my backend support is also called Said. But unfortunately, the speaker Said canceled his talk for today. And backend Said is telling me now, like, oh, I put up a poll. But I think what we're going to do is just to move on to Fotios, who will be presenting his work. And then anyone who has joined us to see Said's talk, yeah, can either stay around to watch Fotios' talk instead. Sorry about that. That's telling me to move on to the next speaker. So Fotios Drakopoulos uses he, him pronouns. He is currently a PhD student with Sarah Verhulst at Ghent University, which is in Belgium. And he's going to be talking about a convolutional neural network of the human inner hair cell and auditory nerve fiber complex. And if you did join for Said's talk, yeah, unfortunately, about that. Fotios?
Right.
I can't, oh, there you are.
Yeah,
I was just going to say, I can't see you.
Let me just set it up. All right. Thanks for the introduction. Good morning, good afternoon to everyone. Today I'm going to talk about our modeling of the inner hair cell and auditory nerve fiber complex using convolutional neural networks. So over the years, the classical approach for modeling biophysical systems is using analytical mechanistic descriptions, and it has undoubtedly improved our understanding of how individual neurons operate and process such information. Although such mechanistic models are able to accurately capture the nonlinear and adaptation properties of sensory systems, as in the case of the auditory system, these descriptions are limited by the scientific knowledge and the hypothesis of the researchers, often incorporating complex relationships such as coupled sets of ordinary differential equations to describe even small neuronal systems. So this mechanistic approach actually results to models that are non-differentiable and are slow to compute, making it rather difficult to advance this framework to model more complex behaviors or large-scale network circuits. On the other hand, the emerged deep neural networks have been proven able to quantify complex behaviors of systems and can be used to construct large-scale networks. The major drawback, of course, of these approaches is their data-driven nature, requiring vast amounts of data to accurately describe such an unknown system. So to address these issues, we present here a hybrid computational modeling and convolutional neural network framework, where existing analytical biophysical neuronal models are used to simulate neurobiological recordings to provide a large and reliable dataset for training DNA-based models of sensory cells and synapses. The present framework was applied to the auditory system to offer Conir, a fast and differentiable model that simulates auditory inner hair cell and auditory nerve fiber processing as accurately as conventional analytical Hodgkin-Huxley and diffusion store models do. The hybrid approach that we followed was to use a state-of-the-art model of the auditory periphery, to which speech stimuli were given as inputs to extract the simulated outputs of each stage of the ascending pathway up to the auditory nerve. For modeling each stage, 201 frequency channels were chosen, and the outputs were sliced and downsampled to form the training input-output datasets. These datasets were used to train different encoder-decoder CNN architectures, specifically designed for each stage, each time minimizing the absolute difference between the simulated and trained outputs. So after training, each of the models was evaluated on the basis of key inner Herschel and auditor nerve fiber complex properties described in experimental studies, using basic stimuli which were not included in the training set. What I won't be talking about today is the first stage of the periphery model, which is a transmission line model of the cochlea and which is already modeled as part of our previous work. If someone wants to know more about this, you can read our archive preprint mentioned here, or you can find the model itself on our GitHub page. Instead, I will focus on the next two stages of the auditory periphery, and I will start with the inner Herschel transduction model, which simulates inner Herschel receptor potential in response to basilar membrane vibration inputs using a Hodgkin-Huxley type description. The end-to-end encoder-decoder architecture that was used for the inner Herschel module consists of 6 CNN layers with strided convolutions. The first 3 layers form the encoder, where the temporal dimension is halved after each CNN layer, resulting to an encoded latent representation. The last 3 deconvolution layers form the decoder, which doubles the temporal dimension after each layer to reobtain the original temporal dimension of the input, as shown in this figure. Different combinations of activation functions were tested after each layer, etanates and the combination of etanates for the encoder and the sigmoid for the decoder layers. And 2 important aspects that constitute these architectures is the context provided to the sides of the inputs to represent prior stimulation and also avoid discontinuities at the boundaries of the simulated outputs, and the skip connections, which ensure that the signal's phase information is preserved throughout the architecture. A cropping layer is also added at the end of the architecture to discard this context information. So after we trained this architecture to simulate inner Herschel processing, we evaluated it on 2 basic properties, the excitation patterns and the AC-DC ratio extracted from the responses. The excitation patterns were computed by the average inner Herschel receptor potential across CF, shown here for the reference inner Herschel model in the first column, and the trained CNN models with the 2 different nonlinearities in columns B and C. The architecture we designed seems able to capture the inner Herschel excitation patterns, with the tanate sigmoid combination shown in column C showing the best performance. The transduction aspects of the inner Herschel model were also evaluated using the ratio of the AC and DC components of the simulated responses in response to tone bursts of 80 dB SPL, and they were compared against the guinea pig data. Oops, too early. The tanate sigmoid architecture predicts well the responses of our baseline model, shows a smooth decrease with increasing frequency similar to that observed to the experimental data. We examined also the growth of the half-wave rectified inner Herschel potential as a function of level, which shows a linear-like increase of the RMS up to about 90 dB SPL. So taking all the results into consideration, we concluded that the Connier tanate sigmoid architecture accurately described all evaluated properties of inner Herschel processing. And now I will move on to the next stage of the auditory periphery, the auditory nerve fiber synapse model, which simulates auditory nerve fiber firing rates in response to inner Herschel receptor potential inputs. The auditory nerve fiber description of the periphery model we used is based on a 3 diffusion store model, and it's comprised by 3 fiber types based on their firing rate, namely the high, medium, and low spontaneous rate fibers. The architecture that we developed for the approximation of the auditory nerve fiber models is one deeper autoencoder, comprised this time by 28 CNN layers. The same architecture was trained for each of the 3 fiber types using the respective firing rate outputs. When compared to the inertial model, a longer input window and longer context was used. Yeah, the choice for the window length and this deep architecture was made so that the slow adaptation properties of the ANFs can be adequately captured, and the longer context was chosen to capture the slow ANF recovery from prior stimulation. 3 activation function combinations were tested, a prelude between all layers and combinations of tanh and prelude and tanh and sigmoid. And after we trained the 3 architectures to simulate ANF processing for each fiber type, we evaluated them by examining the firing rates to tonal stimuli and their level-dependent properties. So the simulated firing rates for each fiber are shown here over time in response to 4 tonal stimuli, starting from top 1 kHz and 4 kHz pure tone and the 1 kHz and 4 kHz amplitude modulated tone. The leftmost column shows the reference responses for the 3 fiber types, and columns B to D show the responses of the trained CNN models using the different nonlinearities. Most of the models show similar performance, but we found that the prelude activation after each layer best captured the firing rates of all ANF models. The second aspect that can be evaluated both computationally and experimentally are the level-dependent properties. The first panel shows the rate level curves computed for each fiber type in response to 2 tone bursts. The dust color curves corresponding to a 1 kHz tone and the solid color to 4 kHz. For all 3 fiber types, the predicted curves of the Connier architecture closely match the ones of the reference models, and they also seem to quantitatively capture the fiber type trends and differences observed in the guinea pig and mouse data. Panel B shows the simulated modulation synchrony of the fibers, computed from the vector strength of the responses for modulated tones of 1 and 4 kHz carriers. Based on both properties and the firing rates, we conclude that the Connier Prelude architectures are able to accurately capture all the evaluated ANF properties. So yeah, maybe quickly I will go through the final aspect that we examined. It was the execution time. After we connected the inner Herschel and outer nerve fiber models together, we computed the average time required to process a single unit cochlear output corresponding to an approximately 80 millisecond speed segment. And we see a significant speed up compared to the reference inner Herschel outer nerve fiber model. And if we connect our previously developed cochlear model as well to this inner Herschel outer nerve fiber model, the full framework can simulate population responses with a latency of less than 13 milliseconds for the same speed segment. Of course, these architectures are parallel, so these models can also be run on a GPU, resulting in a much shorter execution time. And to conclude, we showed that the resulting CNN-based model accurately simulates auditory inner Herschel and auditory nerve fiber processing. It offers a significant speed up compared to the reference model and can be differentiated, making it suitable for backpropagation purposes and applications. When connected to our cochlear CNN model, population responses can be also simulated and be used to drive neural network backends to simulate brainstem processing or the generation of auditory evoked potentials. Finally, further neural network models can be developed on the basis of the presented framework to compose large-scale neuronal models, auditory brain networks, closed-loop-based treatments of the pathological system maybe. But generally, we believe that our framework can be used to advance our knowledge of unknown neuronal systems, such as the brainstem and subcortical pathways or the human auditory cortex. Yeah, and with that, yeah, I'm finished. I would like to thank my collaborators on this project, Professor Sarah Verhulst and Deepak Baby, as well as the entire team of the Hearing Technology Lab. Thank you.
Great, thank you so much, Matthias. That was awesome. So I saw that there were people that actually joined to watch your talk. So just I'm going to rehash what happened today so that they are aware. Our second speaker unfortunately canceled, and instead of waiting for 15 minutes, we decided to move Matthias' talk into that earlier slot. So if you joined to see his talk and you only got to see the last end tail bit of it, then please make sure to rewatch it on YouTube. It was very interesting. And I will now answer some questions, ask you some questions that were posted in the Q&A, specifically from Dan Goodman. Thanks, Dan, for posting your questions. It's really helpful for me. So he is asking, did I understand it right that you're using DNNs to approximate detailed auditory models and not fitting it directly to data?
Yeah, exactly. So the difference of this approach that we followed was that the data were simulated data, actually, that we trained the CNN models to. So we used our auditory periphery model to simulate large data sets to like broadband stimuli such as speech. And yeah, based on this data, we trained our models so we can like create as generalizable models as we can. And yeah, of course, experimental data could be used after training to like further optimize the models, or if we have like such large data sets that we can train our DNN models to, of course, you can use the same directly, I mean, to train them. But yeah, so far, we tried to solve this by simulating all this data.
Okay, so before I ask you the next question that he posted, I'm going to launch a poll about what we should do with the time that we have left. So just when people are interested, they can vote there, and the panelists can vote as well. Matthias, can I ask you the next question, or do you want to look at the poll first?
Yeah, sure, I can. Yeah, I answered the poll already.
Okay, great. I'll ask you the next question that Dan posted. So he is asking, did you peek inside the black box a bit? It will be interesting to know how it's doing the approximation, for example, for things like adaptive dynamics, etc.
Yeah, indeed, this is an interesting question, and this is a nice thing to look at the models. So far, I mean, we know this is a black box, as you say. So far, we haven't really delved into all the details that happen layer after layer and between all the between the architectures. We have an insight about what's going on and what's training to, but of course this is like this is a future work, and we would love to go through this more. Indeed, it's like you can learn, I think, a lot of things through this and what the model actually learned. And yeah, there are so many papers coming that say how you can analyze this CNN models and like more neuronal based models. So it would be something, our future work for sure.
Cool. Sotirios posted me privately a question. Sotirios, would you like to come on and just ask it yourself?
Okay, then. So in your convolutional neural network, what exactly input signals do you pass, and how do you interpret the outputs? Do you pass time-based signals, for example, or are you using spectra or other preprocessing?
So the architectures that we used were end-to-end. So everything is limited to the time domain through convolutions. So what we actually do to approximate every different stage is to pass the time domain, let's say, responses to speech, and get the input and outputs of each stage to the different speech sentences. So everything is in time domain. Everything, we don't examine any spectral or whatever properties. We just let the architecture train based on the time domain signals and learn all the processing and computation steps that it needs to do to transform the output to the auditory nerve firing rates or inner hair cell receptor potential or whatever it might be.
Dan posted another question. So Sotirios, was that the answer you were looking for?
Yeah, I hope so. I didn't ask.
So Dan is asking, can it tell you something unexpected? So I think he's going back to the previous question, right? For example, maybe it learned something about your detailed model that you hadn't realized yourself.
Yeah, this is a nice realization. I mean, as I said, it's actually a bit linked to the previous question. It's actually something like really interesting to start examining this model and to see like what new aspects might come out of this. And I think like these CNN or DNN or these artificial neural network based architectures can indeed give you new insights about the model, or maybe we could learn more about the underlying mechanism or the dynamics of the system. But yeah, as I said, so far we haven't really invested into examining into detail what exactly the model learns and does and what new aspects we could get out of this. But yeah, this would be for sure like something worth exploring. I mean, yeah, it's more or less the same answer that I gave before, but it's something like I know that, I mean, these models like new need novel ways of looking at the, like we should look, I think that these models more like biological systems and not like computational models to analyze them. And this is like a whole new like field of analyzing these black boxes, let's say. So yeah, this would be nice to gain some insight, like more ideas about the models that we didn't get from the computational models so far. All right.
Yes, and it's probably a stretch to ask you if you can speculate on what you expect to find, because then it would be not so surprising.
Yeah.
So most people actually voted to extend the Q&A. I see that your supervisor Sarah is also posting answers to Dan in the Q&A.
Yeah, thanks.
Dan just joined us on stage. I don't know, Dan, if you have any other questions, then feel free, of course, to ask them. Thank you for joining us.
Oop, I think I've got the wrong camera.
You're orange.
Maybe it's the right camera.
Hey, really cool talks, both of the talks actually. I really enjoyed this session. It was perfect for me. Yeah, I'm really excited about this sort of direction of the work, and I love what you've been doing here with the setting up the sort of deep learning version of a much more detailed model. I mean, I think it's already really cool that you can accelerate what you've done, the speed of the models so much. But I guess I'm most excited about like when you can start going beyond that and start learning things about the model that was somehow there and what your models already had, but you didn't know. I guess that's the bit that gets me really excited.
No, I agree. I mean, definitely, it's like, yeah, the processing time benefit is indeed something significant, but yeah, indeed, all the new like ways to look at this after training these models are like, yeah, vast, let's say. I mean, there are many ways many applications or many, yeah, Sarah is here, I see as well.
Hey, Sarah.
I was a bit surprised by the pop-up of the video, but okay, whatever. Yeah, but I think it will be really interesting to see the development, also how like the spiking neural network models, the really large scale networks that like Brian and Sotiris are working on, how that'll interfere with or start interacting with like these very detailed models because we lack some sort of this computation power, and I think it's a step in that direction. I think we're gonna start being able to really start exploring much bigger questions now somewhere in the brainstem or cortex with this.
Yeah, I'd definitely be interested to see if you could like throw in some sort of transfer learning. I think you mentioned it, like you train it up on your model to start with, and then you.
Oh yeah, that's definitely an idea that is easy to like pursue. I mean, once you have a trained model, you can try like using with transfer learning, experimental data and see what happens and see what like, how the architecture changes, for example. I mean, we don't know if it will be as generalizable as before, what will happen, but still, it's like only by analyzing these models, it's exciting by itself. I mean.
Yeah, there are like two aspects in that. Like transfer learning was for us easy in the more peripheral stages to go from a normal hearing cochlea to a hearing impaired cochlea. So you can also think if those higher up neural structures start getting deficiencies, I think you can get transfer learning to actually go from impaired type of deterministic models to get them in this concept. And the other one is, and Fotes wasn't showing this here, but so we've applied this on our auditory nerve fiber models, but we've now also tested the same structure of model onto a number of existing open source models like that. And it seems to work rather well too. So of course the parameters have to change to the specifics of that model, but generally the structure can work for different types of models. So hopefully also other people who have like already mechanistic models available can also use that framework to train their own model. And so when we over time get better deterministic models, because neuroscience data improves, then I think we can easily sort of every time make our fast approximation of whatever is new.
Yeah, indeed, I didn't show that, but it seems that like our method can be generalizable to any other like similar descriptions. So yeah, we tried this with a different inner Herschel model. We tried this with a different auditory nerve fiber model, and it seems to show like, yeah, once you select like a proper architecture that can like simulate and capture all these properties that the specific mechanistic models have, yeah, it's easy to use it with other models or yeah, other descriptions and everything.
That was
Cool.
great. Thank you so much for joining us, Dan and Sarah. I'm going to don my mask one more time and thank the speakers for their participation.
Yeah, we didn't dress up, unfortunately, but yeah, you do it for all of
Let me show you my NeuroMatch t-shirts.
us.
All right.
You can't get them both in the picture. There. Thank you all so much. Let's thank the speakers again. Matthias, thank you so much for your interesting talk. The same to you, Satirius. Good luck with Ian. I'm very excited about everything that's going on in this field. And thank you so much for joining us. I hope you have a really nice Halloween and a good weekend. Thank you so much. Take care all.
Thanks, Dan, for organizing this.
Thank you. Bye-bye.
I did as part of, at NYU, as part of a BRAIN initiative funded collaboration between NYU and Utrecht University. So neural activity in visual cortex varies dynamically over time. When I show you a picture and then I record activity in your brain, I will see a response unfold that usually has multiple complex components. For example, I might see an evoked response as well as an increase in high frequency power. And importantly, the response is changing dynamically over time, even as the stimulus is not changing. In the real world, of course, the visual input is not static like in this example, but constantly changing as well. So for example, when we're exploring New York City by bicycle, the visual input changes both because we look around and because things are moving in the environment. And this leads to a constantly renewing visual inputs. So it's especially complicated to understand or summarize a system that has both dynamic inputs on the one hand and dynamic outputs on the other hand. And here we address this question by using a computational modeling approach, where we specify the computations that convert a time-varying input stimulus to a neural response time course. And we use this model to predict actual neural activity. So we measure neural activity in patients who were undergoing electrocorticography or ECOG while being monitored for epileptic seizures. So early visual cortex is not often sampled in these patients, but by aggregating across multiple patients, in this case 11 in total, we can get a relatively dense coverage of multiple visual regions. We have 110 electrodes in total here in this data set. We localize these electrodes to visual areas by matching them to probabilistic resonantopic atlases that were projected onto a reconstruction of each patient's brain from their MRI scan. And to induce temporal dynamics experimentally, we showed these patients large contrast patterns that were carefully manipulated in 3 ways. So in the duration condition, a single image is shown for one of 6 durations ranging from very brief to about half a second. And in the ISI condition, the same image is shown twice, but with a gap that ranges from very brief to about half a second. And then finally, in the contrast condition, a single image is always shown for the same duration, but with various contrast intensities. And we included this condition because findings in animals have shown that contrast in fact greatly affects the temporal dynamics of neural responses. So from the ECOG recordings, we extracted a broadband response through bandpass filtering, extracting the power envelope for each band and then averaging across the bands. And this results in a so-called broadband time course. And this time course has a characteristic temporal dynamics. So when the stimulus comes on the screen, the response rises quickly but transiently. As the stimulus is still on the screen, the response starts to decrease to a sustained level until stimulus offset. And next I will show you what will happen to these temporal dynamics when we manipulate the stimulus in duration, ISI, and contrast. So let's take a look at the data from a single electrode. Each row here shows the stimulus time course in the gray boxcar and the electrode's response in the black solid line. And this is measured as the relative increase in broadband power for each of our 3 manipulations. So the top row shows going from a very short duration stimulus to a long duration stimulus. The middle row shows 2 stimuli with a short gap versus a long gap. And then the bottom row shows a single stimulus of a long duration but with increased levels of contrast. So the first thing to note about these data is really that they're very beautiful. So even in a single subject, in a single electrode, we see clear responses to the stimuli, and they increase almost 30-fold. This means that's a 3000% increase in signal change. So we also see clear changes in the shapes of the responses due to the stimulus manipulations. Let's take a closer look at these response shapes by considering the average of a number of electrodes, in this case V1 electrodes. And we can make a number of interesting observations here. So in the duration condition, we can see that this transient response becomes progressively larger as you go from very short stimuli to slightly longer stimuli. But at some point, this response no longer increases, and instead it's the sustained level response that starts to become more pronounced. In the ISI condition, we very nicely observe a phenomenon known as adaptation. So when the second stimulus is very close in time to the first stimulus, the second response is very suppressed. But when the gap between the stimuli is larger, the second response recovers. So it means that it has the same amplitude almost as the first response. And finally, in this contrast condition, we see a lot of changes again, both in the transient and the sustained levels, and also in the time that it takes to reach the peak. So it takes longer for low contrast than for high contrast stimuli. So altogether, what do these data show us? Well, they show us that these temporal dynamics of these neural responses in visual cortex are actually highly nonlinear. So the input was very linearly here, but the outputs, they show these complex changes in the shape, for example, affecting transient and sustained parts of the responses differently for the different stimulus manipulations. So to account for these complex temporal dynamics, we fitted a computational model that was previously developed in our group by Jing Zhao and Winnower colleagues. And this model takes a stimulus time course as input and predicts a neural response as output. And this is called a so-called linear nonlinear model. So it has 2 main components, a linear stage that captures the input transient, and then a nonlinear stage that captures the sustained response through a delayed divisive normalization. And as I will show you next, this nonlinear stage is really critical in order to accurately predict these ECOG data. So here we have the data again, shown in black, but now on top of that I've plotted in blue the response prediction from a model that is just the linear stage. And clearly this model does not do a good job. It doesn't get the shape right. For example, here in the long duration, it doesn't get the peak amplitude or the sustained amplitude. And also it doesn't get this decrease for the second stimulus changing over for different ISIs. So here the model fits for a model that has the additional normalization step, and clearly this model provides a much better fit to the data. It nicely captures the response dynamics in all 3 conditions. It's not perfect, that's good to point out. For example, it underpredicts this second bump a little bit, but it's still doing much better than just a linear model. So what I showed you before was more of a sort of schematic, and this is really the full model. delayed normalization, or DN model is what we call it. And it may look, a bit complicated, but in fact it has only a handful of parameters, about 7, of which most really have to do with getting sort of the shape of this initial transient response, the impulse response function, correctly. And then there are a few nonlinear steps. So there's a rectification step, an exponentiation step, and then normalization. And in computational modeling of neurophysiological signals, these are known as so-called canonical computations. And the key innovation of this model, relative to previous models, is that the normalization here is implemented with a delay. So that's what you see here. The response gets divided by a low-pass filtered version of itself. And what this low-pass filtering had, the result of that is that the normalization doesn't kick in until after the response has started. And this ensures that the beginning of the response is kind of dominated by this transient, but then it levels off to a sustained level due to self-normalization. And the advantage of having this explicit model with these different components is that we can go and look inside and see which of these components are really necessary to account for our data. So we can do this through formal model comparison by looking at how cross-validated R² changes as we build up the model. So we see here that for all of these canonical nonlinear operations are kind of leading to improvement in the cross-validated R². So, and it also shows that it's important that the normalization is delayed, because in fact non-delayed normalization does not improve R². And we did this model comparison not just for V1 but also for other visual areas. So in this data set we in fact have good coverage of many visual areas up to TO2, and we find that the model also performs well for these visual areas. And interestingly, we see that the relative improvement for the nonlinear versus linear model increases, being about 1/3 for V1 or V2, up to 50% in TO2. And looking across the hierarchy, we see really interesting differences in temporal dynamics between visual areas. So based on summary statistics computed from the model predictions, like for example the change in the time it takes to reach the peak, we can see that the responses rise more slowly as you come up the hierarchy. And they also stay up longer. We can look at that by comparing the level of response at sort of offset compared to the peak. And that number also increases, meaning that they stay up for longer. So what does this tell us? This tells us that higher visual areas have bigger temporal integration windows. And we can easily see this in the data by just looking at the time courses. So here I'm showing you the data from V1 again, that we looked at already in the solid black lines, but now on top of that I've plotted in dashed lines the responses from area V3b, which is a higher visual area. And you clearly see that the responses rise more slowly and also decrease more slowly. And this is integrating information over a longer time period. And this difference is really nicely predicted by the DN model, as you see here in the red, the model predictions for these two different areas. So to conclude, what we find? We found that neural responses in visual cortex show systematic nonlinear modulations to variations in duration, interval, and contrast. The delayed normalization model simultaneously predicts all three of these temporal dynamics. And the model captures the increased nonlinearity along the visual hierarchy, revealing longer temporal integration windows for higher compared to lower visual areas. I just want to note, so this idea of this increased temporal window length, has been around for a while, and it's been proposed by other groups. And here we show that we can measure it and predict it computationally in human intracranial data. With that, I want to thank everyone who was involved in this project, and you can always email me or reach out for questions. And I want to thank you for your attention.
Fantastic. Thank you, Iris. And in lieu of applause, because we can't do that on Zoom, I'd like you to drop some praise in the chat if you enjoyed the talk. So we have a few minutes for questions here. The first question is from Mark Lescrard, and he is asking, in the single subject, single electrode plots you showed first, there seemed to be some hint of periodicity in the evoked responses. This got a bit washed out in the average plots, as if whatever periodicity is present might vary across subjects or electrodes. Do you think this periodicity might be real? Any comment on it? And Jason Samaha is having a similar question.
Oh, that's interesting. So, of course, it's tricky to base conclusions on just a single electrode. I showed it obviously because I wanted to illustrate how nice it was on the sort of single electrode level. But so I'm not sure how to think about rhythmicity here, because this is in the broadband power, so it is already the power across a wide range of frequencies. It's not the voltage, and so that would mean that there is sort of systematic, rhythmic changes in the power across multiple frequency. Maybe some kind of coupling between high frequency, because we're taking between 60 and higher bands with, say, a lower frequency band. And I don't have very clear ideas or reasons, interpretations of that type of coupling. But I'd be happy to hear suggestions from people who are more knowledgeable about that.
Great, thanks. And Jason was also asking, are the data available with a winky face?
Not yet, but they will when the paper is out. I'm still, writing it up. But if it's out, then we'll make all the data available, and that's precisely the point of this Brain Initiative grant, also to provide these, high-resolution, unique, time-varying data, and that it's to be used for, model testing and model development by anyone who's interested.
Fantastic, thank you. We actually have a lot of other questions, but unfortunately we are out of time. So if we have time at the end of the session, we can answer some of these, but I encourage you also to just respond in the Q&A box if you feel the need. And so we'd like to thank Iris again for the great talk, and we will now move on to the next speaker in this session. And that speaker is Maxine Sherman. Maxine is a postdoc at the University of Sussex. And today she is going to tell us about accumulation of salient perceptual events predicts human subjective time. And so Maxine, whenever you are ready, please take it away. Looks good.
Is it showing up okay?
Yeah, looks great. Here we go.
Right, lovely. Oh, there we go. So usually most models of time perception, their goal is to track clock time. So
actually, hold on, Maxine. I'm sorry to interrupt you, but we've got, oh, there, now it's come through. It just looked a little funny on my end. It looks okay now. Never mind.
Okay. So most models of time perception, their goal is to track clock time or veridical time. And to do this, they usually recruit specialist mechanisms such as pacemakers, for example. So neural mechanisms which can track often through dynamics, veridical time. But the problem here is that they don't intrinsically account for context effects. So one example would be when we say something like a watch pot never boils, because we're doing something particularly boring, time feels like it's passing very slowly. So the proposal here was that time is estimated from the outputs of sensory processing. So from the beginning, the assumption is that content and time are intrinsically linked through perception. And the duration is estimated from the number of salient events in an epoch. So just to illustrate this, suppose we have an epoch here, so it starts at the green and finishes at the brown. And these colored boxes are salient events. And for example, if we are on holiday, these might be exciting things that we've done. And so within an epoch, here we've got lots of salient events. The assumption would be here, lots of salient events means lots of time has passed. And then by contrast, in this epoch, very little is happening. So people would rate the epoch as not having lasted very long. This isn't about the speed of time. This is about the actual rating you would give to how much time has passed. And so we tested this proposal in 40 participants. So people watched naturalistic videos, either of an office. So this is literally the camera is sitting on a desk and almost nothing is happening because people are working, versus city videos. So an RA walked around Brighton town centre. You see different shops, you see people walking past, much more interesting. And they have varying duration. And people simply needed to rate how long they thought these videos were. Super simple and pre-registered. So the key measure that we're using here is just participants' bias towards overall underestimating duration. So we weren't interested so much in how good people were at tracking time, but rather, could we predict when it feels like something is long and when it feels like something is short. So hereby it's just people's report for each video relative to their mean report for that duration, standardized. So what happened with behavior? The key point here is that if you contrast these busy city scenes where lots was going on, people rated them as lasting longer relative to these boring office videos where nothing happened. So far, more stuff equals more time. And so the first step was to say, okay, so if we feed a classifier these videos, can we actually extract salient events from the videos, and does that reproduce this effect? So we fed this convolutional neural net, AnnexNet, pre-trained to do perceptual classification. We just fed it the same videos the participants watched, got node-wise changes in activation. So for each frame, how much has each node in AlexNet changed? These are the changes, like those boxes I showed before. And in order to say, well, was it a salient event? We just used a criterion. It really doesn't matter how you set this, it's always the same. But I can go into more detail if you want. And then that gives us for each video a number of salient events, but they are layer by layer and in an obscure unit. So in order to transform them into seconds, just use support vector regression, mapping these changes onto the veridical video duration. So it would have been trivial to regress it onto what people actually said. Instead, we regressed it onto clock time, if you like. And then we can see, what does this model predict? So very much like the human behavior, if you extract salient events, whatever they may be, from the video stimuli themselves, again, AlexNet would predict an overestimated report for these busy city scenes and an underestimated report for these boring office scenes. So far so good, but the problem is that the human brain is not AlexNet. So we did this with fMRI. So exactly the same process. The only difference is that instead of using node activation in AlexNet, from AlexNet, we're using voxel activity in human visual cortex. So this convolutional neural net we used before has layers. We had layers here as well. So again, pre-registered. So we're just going from V1 up to higher level visual areas. We extracted just the voxel bold and computed the difference between each TR, the bold difference between each TR. And then that gives us here, so say these are all the TRs for one video. We categorize them as salient or not, and again, regress them into units of seconds. So now we're just trying to predict subjective time purely from visual cortex bold. But just to quickly explain what changes here. So the one we pre-registered, it's just the Euclidean distance. So the assumption is change, a salient event is constructed on top of the raw bold signal. So you just subtract them and take the absolute value, and that's how much voxel activity has changed. We also did an exploratory version where we said, okay, well, maybe bold already signals change, for example, these prediction error-like responses we often see. So you just don't take absolute value. So what happens in visual cortex? Well, we find the same thing again when you do the pre-registered measure. Oh, sorry, when you do the exploratory measure, not the pre-registered measure, where these time estimates constructed from visual cortex are overestimating time for these more interesting videos relative to these boring videos where nothing happens. But in both cases, you get this trial by trial correlation. So for each video, you can predict what people will say in terms of over or underestimating time purely from their visual cortex bold. maybe this is like a global effect, but it's not, because if you do this in auditory cortex, it doesn't work with either the pre-registered or the exploratory. And same for somatosensory cortex. So this is not general to sensory cortices. This is specific to these silent videos. I should have mentioned before they were silent. These silent videos that we used. So the idea here is that because we could predict over or underestimates of time from visual cortex, but not from these control regions, that we can produce then an algorithm for how we construct subjective time just from perceptual processing without having to appeal to clock models or any specialized processes. I think maybe I went a little fast, but thank you to Warwick, who came up with this whole model, and Zaf and Anna.
Fantastic. Thank you, Maxine. And in lieu of applause, again, please drop your praise in the chat if you enjoyed the talk. Fantastic. So while we're waiting for a couple questions to come in, I actually have a question, if I might, because we've got a couple minutes. So this is really cool, and thanks for sharing it with us. I was wondering, you said the fMRI is whole brain, correct? So where then are you looking, or would you expect to find kind of a more cognitive correlate of subjective time if you were to go look in these data that you've already collected?
By cognitive correlate, do you mean this kind of general GLM, or what do you mean by a cognitive?
Yeah, like either a general GLM that's kind of monotonically related to subjective time, or a place where maybe you could even use a multivariate approach to decode subjective time, maybe in more frontal cortices or something like that.
Right, yeah. So in terms of where you can, where you see effects of just the bias in time, we saw it in a couple of frontal regions, also in visual cortex.
Mm-hmm.
But I suppose over and above this process of just accumulating these salient events, you need to do things like report, translate it onto a scale, all sorts of other processes that might end up recruiting frontal cortices. But yes, we did find visual cortex, which I was surprised about.
Fantastic. Cool. I have more questions, but I will cede the stage to the folks that are coming in with the questions. So the first question that we have here is about this talk is from Martin Weiner, or Weiner, I'm not sure which, sorry. Very cool. One question. Do we think visual cortex also stores memories of durations as well? Are there implications for cross-modal transfer?
So this is a really interesting question, and one that Warwick would be so much better at answering than me. I am not aware of memory of neural correlates or otherwise of memory and visual cortex. I would imagine you have other regions for that. This is the kind of work that Warwick has been following on with, trying to bring in memory into this model, because obviously when you're accumulating changes, especially over longer events, for example, in episodic memory, you need to actually, yes, you need memory. But I don't think visual cortex would be the case. Warwick is the one to answer this one. Sure.
And if we have time, we can actually hand Warwick a microphone. I see him in the audience here. So let's pause on that one and get to the last question here. And maybe if we have time, we can bring him up on stage if he's willing. So Dobie Ranev is asking, very cool. I was wondering though, could there be other things that are different between office and city scenes? Could you get similar results if you analyze separately the more versus less dynamic city scenes?
So it's a difficult question to answer, because it's basically the primary point of the model is that the more dynamic they are, the more changes there are. And that is what we are using to construct time. So it's not really that the amount that they're seen as dynamic is some sort of confound or something separate to it's the core point of the algorithm that we're using, that it is exactly the extent to which they are dynamic and they are changing that is constructing this sense of time. And so with the AlexNet analysis, for example, you would absolutely see that between different videos, you're having maybe the office or the city scenes might vary more or less than the others in that category. And that seems to be exactly what is driving these overall underestimates of time, the amount that they're changing.
I think if I might follow up, I think what Dobie is asking is also about whether there might be differences in, for example, spatial frequency distributions or other elements that are kind of different between, and Dobie, you can tell me if I'm totally botching this, but if there might be other things that are really quite different categorically between the office scenes and the city scenes, that if you just use the city scenes, but then looked for dynamic changes or amount of dynamic changes within the city only category, would you still see this?
So we haven't. So one possibility would be to kind of just take this the city scenes alone and, you know, map them to the AlexNet responses.
Mm-hmm.
But yeah. I still think that the primary point is even changes in spatial frequency, which would be detected by visual cortex, would also comprise some of these salient events that would be picked up on. So, you know, at the very lowest levels of processing, for example, spatial frequency changes, these are exactly what we are proposing as driving the differences in over underestimating time. So I completely understand the point. I'm just saying, I think from our perspective, we don't see them as something separate. They're the core point of the algorithm.
Great, thanks. So unfortunately, it looks like our third speaker was not able to join us today. So what we can do here is we can actually have a slightly extended Q&A if the speakers are up for it. And if other people have any unanswered questions as well. And one of the things we could do is hand Warwick a microphone if he is wanting to talk about the visual memory question. But if you have other questions for Iris, we can also do that. Or if you'd like to follow up on anything that was put in the Q&A box. So the way we can do this is if you raise your hand, we can essentially just hand you a microphone and then we can have a conversation about it. So Maxime, do you want to keep your slides up? Actually, let's hand Warwick a microphone here. Maybe he can answer the memory question if he's willing.
I think there's a message now from Matthew in the chat. He said,
okay, never mind. You're right. So let's do this offline. And Matthew, we will go ahead and get you here. So here we go. All right. Matthew, you are now a panelist. Fantastic. Okay, never mind, Warwick. I'm sorry to get you up here on stage, but Matthew, why don't we go ahead then? Great. Awesome. So Matthew Schinkel is from the University of Nevada, Reno, and he is a PhD student. And he is going to tell us about body part and location selectivity surrounding human MT plus or human MT in bold responses to naturalistic stimuli. So please, Matthew, take it away.
Awesome. Thank you. You can see my screen fine. All right. So thank you, everybody, for coming. We actually spend a lot of time in our everyday lives looking at bodies. And this is because bodies can tell us a lot of things. Everyone from stage actors to advertisers to animators know that you can convey a lot about someone's intentions and communication and emotions just from the positions of their body parts. And so this raises the question of where bodies and body parts and their positions are represented in the brain. There are a few regions of cortex that are well known to be selective to bodies and body parts. These include the fusiform face and body areas, the occipital face area and the extrastriate body area. But there have been a few papers in the last decade that have added nuance to this description. For instance, Orlov, Makin, and Zahari in 2010 showed participants images of isolated body parts versus control images and found selectivity to not just bodies, but specific body parts, forming this sort of patchwork across a large portion of lateral occipitotemporal cortex. Weiner and Grossbecker in 2011 did a similar study, but found that body selectivity was generally circumscribed to a region around HMT, a region of cortex known to be selective to motion. And they found that body selectivity could generally be described as 3 distinct clusters with selectivity to different body parts and visual field locations. Ferry, Kolster, Zastrov, and Orban in 2013 used maps of retinotopy and motion selectivity to determine the degree of overlap between motion and body selectivity around HMT, finding a large degree of overlap in this region. And so this raised a few questions that we were interested in investigating. We wanted to see whether we could predict bold responses to naturalistic stimuli based on body information. We wanted to determine the degree of overlap between body and motion selectivity, specifically around HMT. And we wanted to see whether body selectivity around HMT could actually be described as multiple body selective regions with different tuning to different body parts and visual field locations. So to address this question, we used 3 sets of naturalistic stimuli: a set of static natural images, a series of dynamic naturalistic movie clips, and a set of computer-rendered scenes with a camera smoothly panning through the environment. For the fMRI data in response to these stimuli was collected for a number of previous studies, but for 3 of our participants, we had data for all 3 of these sets of stimuli, resulting in over 9.5 hours of richly varied naturalistic stimuli that are closer to visual experience than stimuli used in previous studies and conventional localizers. In order to extract body information from our stimuli, we used OpenPose, which is a deep neural network that extracts the locations of body key points from images or movie frames. And so a key point could be, for example, an elbow or a wrist. And then we use these key point locations in order to infer the locations of larger body parts in our stimuli, specifically the locations of faces, trunks, arms, hands, legs, and feet. In order to characterize the extent to which voxels are selective to these features, we employed a voxel-wise modeling approach. And this involved fitting a separate model for each participant and for each data set. To do this, we split our stimuli into training and testing stimuli. We used the body features and bold responses of a single subject in order to fit model weights using ridge regression. And here there is a model weight relating each voxel in a participant's brain to each one of our training features. We then use testing body features, so features from our testing stimuli, and multiply these by our model weights in order to predict bold responses at each voxel in the brain. We then computed the correlation between our predicted and observed bold responses at each voxel in order to generate a map of how well we can predict each voxel in a participant's brain just knowing these body features. So what this resulted in for each participant was 3 of these maps, 1 for each experiment, of prediction accuracy at each voxel. But because we wanted to combine data from all 3 of our data sets into our analyses, what we actually did was then average these flat maps into a single average flat map for each participant. And so here we have the average prediction accuracy across data sets for one of our participants using our body model. And so as you can see in regions such as FFA and OFA, we see fairly high prediction in voxels, which makes sense given that our model includes face information among other body parts. If we look at this region around HMT, we see very poor prediction accuracy toward the center of HMT, but relatively high prediction accuracy in voxels surrounding HMT and extending toward PSTS. And so all of these voxels are potentially selective to bodies. But because we're using naturalistic stimuli, specifically 2 data sets that include motion as well, there's a good chance that our body features are correlated with certain types of motion. Think, for example, when you're walking, your arms tend to be swinging in a different way than your shoulders or your feet might. And so this raises the question of whether this is real selectivity to bodies. So in order to determine whether this is actually body selectivity, as well as to ascertain the degree of overlap between body and motion selectivity, we also extracted motion features from these same stimuli. To do this, we use spatiotemporal gabors that vary in location, size, spatial frequency, direction of motion, and speed of motion. So as you can see in this video, we captured a very detailed picture of the motion in our stimuli. We then fit 2 additional models, just like our body model, one using just motion features and one using both body and motion features. We computed prediction accuracy at each voxel for these models and squared these prediction accuracies to determine the amount of variance explained in each voxel by each of these 3 models. We then used a form of model comparison called variance partitioning, in which we subtract the variance explained by our individual models from the combined model in order to determine how much unique variance each of these 2 models contributes to our prediction of brain responses. Note that this also enables us to compute the amount of shared variance between these models, but we won't include these in the subsequent flat maps, though I have these in supplementary figures if you're interested in seeing them. So this is a visualization of the amount of unique variance explained by our body model and unique variance explained by our motion model in each voxel. If we look at regions like FFA and OFA, it's almost entirely orange, which corresponds to unique variance explained by our body model, but no unique variance explained by our motion model. In contrast, if we look toward the center of HMT, these are almost entirely blue, indicating a high amount of unique variance explained by our motion model, but very little by our body model. And if we look at this region surrounding HMT along this border here, we see a lot of white, which indicates unique variance explained by our body model and other unique variance explained by our motion model. So this confirms that these voxels are actually selective to bodies, but that they're also selective to motion independently. Finally, we wanted to see whether these body selective voxels could actually be described as a few functionally distinct subregions. In order to do this, we used the weights that we fit in our voxel-wise model. And so if you'll recall, we have for each voxel in the brain, weights relating how much that voxel cares about each of our body features. And so if we look at a voxel in FFA, for example, we see very high positive weights for faces, but very close to 0 weights for other body parts. And so what we did is for each voxel in the brain, we averaged across visual field locations for each of our 6 body parts. So what this resulted in was 6 averaged values representing in general how much each voxel cares about each of our 6 body parts anywhere in the image. We then said which of these values is the highest, just thus telling us which body part each voxel seems to care about the most. That's what we have visualized here, where different colors correspond to different tuning to specific body parts more than other body parts. And so if we look at FFA and OFA, it's almost entirely pink, suggesting that almost all voxels in these regions are more selective to faces than other body parts. And if we look at this region around HMT, we see a mix of selectivity to a bunch of different body parts, but we can extract some general trends from this. Notably, if we look along the dorsal border, we tend to see a lot of selectivity to feet and some selectivity or to legs in red and to arms in dark blue. If we look along the rostral and caudal-most portions of this HMT region, we tend to see a lot of pink, which is selectivity to faces. And in contrast, if we look along the ventral border, we see a lot of green, which is selectivity to feet, and a lot of blue, which is selectivity to hands. This is generally consistent across participants. So here we have for subject 2, we see a lot of face selectivity, which is this pink, along the rostral and caudal portions of HMT and the surrounding areas. And if we look along the ventral border, we see a lot of green for feet and blue for hands. This is very distinct in our third participant, where especially on the left side, in the left hemisphere, we see tuning almost entirely more to hands and feet than other body parts. Finally, we also wanted to see whether these regions may vary in selectivity to different visual field regions. So we took the average weight for any body part in the left portion of the visual field and the average weight for any body part in the right portion of the visual field. And by subtracting one of these values from the other, we got a continuous metric of selectivity to the left or right portion of the visual field. And so, as generally expected, we see contralateral tuning in a lot of the visual system. And if we look at these voxels around HMT, we see relatively strong contralaterality along the dorsalmost border, but very weak to minimal evidence of contralateral tuning along the ventralmost border. we did the same analysis for upper versus lower portions of the visual field, finding that the dorsal portion of voxels surrounding HMT tend to be lower selective, whereas voxels along the dorsalmost border demonstrate more upper selectivity, which is consistent with retinotopy existing in HMT, but confirms that this holds true for the presence of body features as well. So to answer the questions that we raised at the beginning, we found evidence of body and body part selectivity in voxels surrounding HMT. We found a substantial degree of overlap between selectivity to bodies and selectivity to motion in voxels toward the periphery of HMT, whereas the center of HMT is almost entirely motion selective. And we found some evidence of distinct clusters of body selectivity in this region, with selectivity to different body parts and visual field locations. So I'd like to say thank you to my PI, Mark Lesquois, to the fellow members of my lab and the funding that let me do this project, and to you for viewing. So, thank you.
Fantastic. Thank you, Matthew. And if you enjoyed the talk, please drop some praise in the chat in lieu of applause. So we have one question from Iris here on the panel. So she says, very cool that you can pull all of these selectivities from the naturalistic input. One thing I noticed was that HMT didn't seem more motion selective than, say, V1, V2, V3. Was that expected? And Iris, I will let you follow up as well. Just want to read these out for the folks watching on YouTube and elsewhere.
Yeah, so that's a great question. And this is one of our supplementary figures. This is the amount of unique variance explained by motion. And we raised the threshold so you can, since it kind of just washes out at the threshold we had before in order to show body selectivity. So in a way, this is kind of to be expected because we're capturing a lot, because we're using different spatial frequencies and different visual field positions in our motion model, we're capturing a lot about the low level, non-motion visual characteristics. And this makes it a little more clear as well that we see a lot more unique variance explained by our motion model toward the center of HMT than around here. So this did not surprise us exactly, but it is definitely an interesting finding.
Thanks.
Great. Do we have any other questions for Matthew before we close up the session? Okay.
Another question, if you.
we have a few minutes, like 1 minute.
Well, I'm just curious because we're making quite a bit about that, so that you're seeing sort of on the edge of HMT, you're seeing selectivity, right? So what's your interpretation sort of functionally of that? What do you think? Why is that there? Do you want to say, are you trying to say that, you know, these areas are not as segregated as we tend to think based on the literature? There's more sort of diffuse selectivity, or that it actually replicates the literature really well?
This generally replicates the findings specifically of Weiner and Grossbechter's paper, where they found that body selectivity, they were trying to address this question of, are HMT and EBA overlapping or distinct? And they found this kind of crescent shape around HMT of body selectivity. And that's generally what we confirmed, though the exact shape of this crescent, they found it generally extended along the dorsalmost or ventralmost border, and we find it a little bit more dorsally distributed. As far as the reason for that, that's a great question. And I'm very curious to hear what other people think, because I'm not sure.
Cool.
And that sounds like a good place to end on, because unfortunately we're going to get kicked out of this room momentarily. So I'd like to thank all of our speakers once again for their fantastic talks. This was a really engaging session, and so thank you for being here. And reminder, meet with your NeuroMatch matches and follow up with the speakers if you have more questions, if we didn't get to your question, or if you want to continue the discussion. So thanks again to everybody for being here, and also to our NeuroMatch backend technical host, Hadi Mohamedi, for helping out run the session, and we will see you next time. Thanks, guys. Bye. Of associative evaluations, metacognitive assessment, and self-report, a computational approach. And so Isabel, please enlighten me how to pronounce your name properly.
Yeah, so I'm Isabel Yomshaite. Yeah, I think it's gonna be complicated. That's unavoidable. But yeah, so I'm a master's student in cognitive science, And today I want to share with you a research project that I've completed as a thesis, and I'm in the process of developing it into a paper. So any feedback and questions are very welcome. And I will include my email at the end, so you can actually send me questions as well and share any feedback. So the output of this project is a prototype computational model of implicit and explicit attitude dynamics and their interaction. So attitudes are generally defined as global evaluations of a topic, event, object, or a person. And they are constituted by, but they also shape our beliefs, feelings, and behaviors. So they have this recursive quality. And for these reasons, attitudes have very significant influence on decisions that individuals make, but they also shape democratic societies. So to that end, researchers have produced numerous empirical observations in order to better understand attitudes, but to a large extent, this research has been descriptive in nature due to the linear statistical models as the prevalent methods of analysis. So these linear models can categorize data or test variables for linear relationships. However, they cannot capture nonlinear or recursive processes, which are characteristic to phenomena as complex as attitudes. But recently, we have seen an increase in dynamical systems models that can analytically access these characteristics by way of nonlinear modeling of phenomena at the process level. So such modeling is realized through so-called bespoke generative models. So these models translate psychological theories into computational custom-made mechanisms, which generate synthetic observations, which approximate the processes and outputs of the actual target system. So therefore, we can fit such models to infer the underlying complex processes. So, and implicit, explicit attitude formation processes and implicit, explicit attitude measurements are a good case study of processes and related observations that can be captured by dynamical systems modeling at more depth than linear models. So dual process theories distinguish these two operating systems of attitudes: the implicit one, which is described as associative, intuitive, and spontaneous, and explicit, which is the reflective and controlled way of forming attitudes. And we have measurements that, such as the implicit association test and self-report that intend to capture these corresponding processes. However, these measurements have quite a lot of problems with both validity and reliability. So for example, there's no guarantee that a person who's asked to give self-report about their attitudes is not gonna give spontaneous responses. And we also people have lots of questions about whether implicit tests capture the true attitude, because there could be some bias that is implicit, but the person in their daily life could be just inhibiting and using their kind of reflective attitudes more in making decisions. So the validity is questionable for these assessments. So it seems like it's much more likely that these two processes, implicit and explicit, are interacting in reality, and this interaction is what we tackle in this model. And to tackle it, we propose an architecture and dynamics for this interaction as the minimal sufficient model that can account for the possible underlying processes needed to generate implicit and explicit interacting attitudes. And overall, it should be taken as a formalized hypothesis. So to give a brief initial sketch of the model, it consists of 3 modules, as depicted in this, for now, very simple schema. So we claim that these 3 types of processes are needed to generate implicit, explicit attitudes and their interaction. So we have associative evaluations for the implicit part, metacognitive assessment, plus self-report for the explicit part, and they have all, we claim, bidirectional interaction. And so, but also our approach is we keep this general structure the same, but in our simulations, we have created 3 sample cognitive profiles that each have different weightings for the relative influence from these different processes. And these profiles are sort of operationalizations of different cognitive modes or priorities that, and we in our simulation that I'm going to go through a bit later, we observe emergent phenomena, attitudinal phenomena such as cognitive dissonance, radical belief emergence, or illusory truth effect in some profiles, but not in others. And this model was constructed by using 2 existing frameworks. So I will only have time to overview them very broadly and very briefly, but the model we use for modeling the implicit dynamics is this learning Ising model. So here they take a very simple neural network that can perform computations within this network structure where the nodes have binary values, and the dynamics are consistency driven. So the network tends to converge to either positive or negative values. And this very closely corresponds to how we reason if we reason only in an associative way, and how it is described in the existing theories. So we don't, we make our judgments based on our existing evaluations of relevant other aspects. So for example, if you have formed a negative first impression about someone, you're more likely to assess their other actions also in a negative way. And we have the reverse. If you have positive associations with a person or a topic or an object, you evaluate other things related to them also in a positive way, which is known as the halo effect. So that's if you are in full-on associative mode, and we use this to model this computationally. And the second framework that we use to build on the 2 other modules is the active inference framework. So I cannot introduce you fully to this framework, but essentially it is a Bayesian cognitive modeling framework, which is why we are even able to merge this framework. So it kind of transfers everything into a probability, and it can integrate different sources of information. So the real-time dynamics of the previous associative dynamics, plus it can add the prior and combine them into one assessment. And the specific framework, what is special about it is that it has one overarching principle of self-organization that is driven by entropy minimization. But it is also a hierarchical model and has a buildable architecture, which allows us to take different cognitive processes and differentiate them and how we define them if we specify them on a different kind of hierarchical place. So we also have like this higher level, metacognitive level, and that's a higher level in the hierarchy. So we can differentiate these processes, but they are still integrated under this one principle of self-organization or entropy minimization. So now I can go into a bit more detail on how the hybrid model works in technical terms. So here is the first part translated into, well, it's graphed as a directed Bayesian network, which is the standard way of graphing with an active inference, and it displays all the variables in the first network, and it represents the conditional dependencies between random variables and how horizontally how they develop over time. But essentially, it will not be possible, of course, to understand all these variables, but what is special about this framework is that they are actually all interpretable, so it's very useful to make sense of it. So this is the base model, how it works. So from the perspective of one node, it infers its own state based on the state of the other node, so that's the xj, but its kind of policy of action is the probability that we calculate with the traditional Hopfield network equations. And then we add, so here's this module of associative evaluations represented, and it develops over time. It's still the same model. It's just the next iteration. But here I added now the higher level, which is already the active inference nodes, and as opposed to the lower level nodes that have binary values plus or minus 1, so positive or negative. That's also interpreted in these attitude terms. But here the higher level has probabilistic values, so it holds the it holds the assessment, which is what the base model cannot do. So it has a global evaluation, and it can recursively influence the model's evaluation. So that's the function of metacognition, to partially evaluate it. So I can see that I have to finish quickly. So then, yeah, we use the precision terms to adjust the difference, to make up the different profiles. And the 3 profiles that we have is the inoperative metacognition, so where the agent doesn't rely on this information, where they just think associatively; functional metacognition, where metacognition partially informs their decision; and overconfident metacognition, where the agent over-relies on the information. So I will have to just jump through the 3 simulations. So basically, we observe cognitive dissonance in this causal intervention, where we expose 3 agents to negative information, but only this profile lags behind. So we see divergence between these assessments. And then the second simulation shows that forced self-report, if an agent has to continuously self-report, that actually contributes to radicalization of beliefs. And then the third simulation shows that it's about forcing to give a specific report, which is similar to what we would observe in like social pressure to have certain beliefs. And then we see that some agents, but not others, adopt these beliefs that were not unique to them. So this is how, and you can observe more detailed interactions more precisely in the graphs. But to sum up, what is interesting about this model is that we suggest possible processes for these attitudinal phenomena as a result of interaction of explicit and implicit processes. But overall, our approach is to try and think what is actually happening. It's we don't want to explain them as a result of just inattention or irrationality, but we want to imagine what is going on in a phenomenological sense in an agent that has these things as a result, but perhaps they wanted more stability, like some agents wanted more stability over time, and then others wanted more stability on other levels. So it's not just consistency between the elements, but there could be more consistencies as a cognitive goal that could explain these different outcomes of attitude processes. And yeah, I will not cover the limitations or everything to just finish quicker, but it's just a prototype model, so there's a lot of work to be done with it. And yeah, thanks for your attention. And here's my email if you want any questions.
Great, yeah, thank you. This is really interesting stuff. Thank you so much, Isabel, for the fantastic talk. We have about 45 seconds for a question. So because I don't see any questions coming in, I will actually ask a question. I'll take this opportunity. So the difference between your non-functioning metacognition and your functional metacognition seemed to be binary, that it was like either it really is working or it is not working at all. There's no metacognition. Is there any room for kind of metacognitive noise in there? Maybe it was too fast and I didn't get that detail. But where does the metacognitive kind of noise come in, like suboptimal or like imperfect metacognition as opposed to all or none?
Yeah, so actually the way these profiles are constructed is that we just chose certain precision values as weightings, and I just claim that these are categories, but actually they are continuous values. So if we wanted to scale this model up to society level, we could actually draw from this possible distribution, and we could have agents with completely varying levels of how much metacognitive kind of assessment you rely on, and how much you kind of process only things real time and depending on the real time associations. Cool, thanks. And it was probably in there, but I missed the detail. So thank you. I appreciate it. Yeah. Thank you. Okay, so unfortunately for time, we do have to move on. But if you guys do have questions for Isabel, please put them in the Q&A and then we can answer them in threaded form in text. And if we have time at the end, we can go through them as well. So thanks again, Isabel, for the fantastic talk. That was really interesting. Thank you. Thanks. So our next speaker now is Arun Kumar from the University of Minnesota. And he is going to tell us about knowledge-centric metacognitive approach for solving tasks. So Arun, please take it away when you are ready.
Looks great. And you need to unmute. Hold on. There we go. All right.
Hi, Megan. Thank you. And first, I would like to thank organizers for giving us the opportunity to talk about our work, although it might be in progress work, but it's great. I'm really excited about it. So in this discussion, we are going to talk about our proposed framework, which is knowledge-centric metacognitive approach, and how we can actually think of using that to solve the tasks. So this is work along with my advisor, Paul Setter at the University of Minnesota. Let's first talk about what are the kind of issues that we have with the AI agents right now. So there are a lot of progress which has been made in AI agents, but there's some fundamental issues. And one of the fundamental issue that remains is generalization. For example, let's take some really basic examples. So people can, for example, go and cook food, then at the same time, the same people who can really go and do some work in their labs, people can go to their friend's house to really look at some aspect of the task they are kind of involved in. And then it's the same person who might really go to orchestra hall to do some different tasks. People are really flexible in the way they do things. So it is one important part of human intelligence, the flexibility of doing different or a variety of tasks. And apart from that, like if you look at, there are like a door at the top and there are different type of doors at the bottom where people might really enter. Although they look very different, but still they are the doors. So people really understand how to really interact, that they can really open those doors. So people really understand this part. But this is fundamental issue with AI agents right now, because they tend to learn end-to-end task-specific representations, which really does not have the generalization or flexibility capabilities. So what we are trying to propose is that there is a natural way of doing the abstraction. And this high-level knowledge is the one which is actually driving the low-level interaction. So people are, or the agents should actually learn by interaction with these objects rather than trying to learn this end-to-end task-specific representations. So that's our proposal. So now let's actually give little brief about how we really think about it. So let's look at agents' knowledge. So agents' knowledge of the environment consists of entities and the relations and basically the rules of the environment, but that is at very high level, at the type space level. So what is the instance level? Instance levels are the instantiation of the type level knowledge that agent has, but that is instantiated based upon the current state of the environment. So how does the task solution really going to work in this scenario? So from the high level, agent is going to really have an activation of what kind of interaction it might have a particular type of object, and use that to really form a proposal or form an activation recommendation to the lower level. And that lowest level is the one where agent is really going to actually execute the policy. But now instead of looking at the end-to-end policy, it's going to really it's going to really form a repertoire of policies which are specific to interaction for those particular objects, which were driven from the top level, from the high level, from agent's knowledge of the environment. And then by making this repository, this repertoire of these sub-goal policies, agent can really now form a solution of the task by composing them in different ways. So this process actually, that's what we are proposing, that it actually provides the flexibility of the environment. So let's now look at some small illustration of the thought process that we have. So this is a procedurally generated mini grid world. We chose it because it has these different components, different ingredients which would be required for this high level processing. So for example, like here the triangle one is the agent, and there are these different doors in the environment. Now these small ones over here, they are the boxes, but the keys, like some of the doors are locked, some of the doors are unlocked. Agent does not know about it, but some of these keys are hidden in these boxes. So agent's goal is to go from here to start with, and goal is to really pick up the blue ball. That's the agent's goal. But it has to reason about this different path. There are different type of, for their doors, they're different doors, but still they are of the door type. So what we are going to really illustrate here briefly, okay, so this is the initial state. And if you look at it, is partially observable environment, and environment like agent just had an observation of this particular part of the environment here. So next system, what it does, it tries to really interact with the door. So what kind of interaction it might have with door? It can open the door. So it's going to learn now how to open the door rather than trying to learn everything, end to end. It's going to really just look at this part. Then, so basically these are the steps that first it tries to learn that can it open the door. It need to reach the door in order to be able to do that. And then it learns that it can open the doors. So these are the sub-goal policies that the agent is learning. Now, as a next step, so after opening the door, now it sees that there is an obstacle. There is green ball over there, which is sitting in front of this other door. So it needs to remove that obstacle. So next step is just to learn how to remove those obstacles. But that is a sub-goal. That's the way it's going to really interact with the green balls. So it picks up those balls and drops them. Now, after it is dropped, now this door is locked. So agent has to kind of find out where the key could be. So the key is somewhere hidden in the box. So it needs to really reveal the key. So it has to learn how to toggle the box. So that's another small interaction part. So once it has learned how to toggle the box, it can do the same thing again and again in any different similar kind of setup. If the way it has learned how to open the door, it can go ahead and open the door anyway. It can reuse from the same repertoire of sub-goal policies. Then the next step, it just goes and reveals the key over there. So it reveals the key and it picks up the key. Then once it has the key, it can go ahead and open the door. And after opening the door with the key, now it knows that they can be, for door locked, it can really go and learn a sub policy to open it with the key. So then later it can just go and drop the key because it needs to pick up the blue ball. And as a last step, it can really go next to the blue ball. So basically what we are trying to illustrate here is that by learning the separate interactions over there, these interactions are driven from the type space, which are dependent on the type rather than at the very low level. So we can really form a flexible way of solving the task by composing this lowest level sub-goal policies. And it can really bootstrap for solving new tasks using the same kind of repertoire of policies. So that's what we actually have in mind. It's still work in progress. We are still trying to learn it for different tasks, but that there's a natural way of abstraction of the way we see. And one of the fundamental part of our thought process is that it is based on the interactions that we have, and knowledge graph at the higher abstraction, it drives the interactions at the low level. Then at the low level, we learn sub-goal policies, and agent can reuse those low level policies to solve a variety of tasks. So there's like many things that I still need to kind of finish on that part, but that's the basic idea that we have. And thanks. And then I am actually, if there are any questions, I would be glad to take them.
Fabulous, thank you. And in lieu of applause, I forgot to do this last time, but if you enjoyed the talk, please drop some praise in the chat because we cannot clap and it feels a little sterile. So thanks very much, Arun, for the fantastic talk. We have a few minutes for questions here, which is great. So if you have any questions, please use the Q&A box at the bottom of your screen, or you can just type them in the chat if you prefer. And if you'd like to follow up on this, these are our interactive talks. So you can also raise your hand using the raise your hand feature, and we can actually hand you a microphone and you can have a back and forth. And we have one question here from Quan Do. I hope I pronounced that correctly. And so the question is, how is the knowledge graph formed in the first place? I would imagine lower level action informs higher level graph. And Quan, I'm going to also hand you a microphone because this is an interactive talk.
Yeah, I read that. So basically, the very first thing at the type space level, we assume that it is at the type space level that it is given. But the first instantiation is from the low level, and because this our environment is procedurally generated, we go ahead and generate that low level instance graph. But that is part of the object recognition system. Now, one of the basic thing that in current RL agents are really doing is they're trying to have object recognition as well as the reasoning and task solution all together. But we assume that an object recognition system exists. Like given that you have a particular environment, like agent is able to recognize the objects and whether the objects are together or far away, those kind of basic relations. So yes, it is actually built from the environment using the recognition systems. I hope that answers the question.
Yes, thank you.
Oh, I'm sorry. I forgot to mute myself or unmute myself. We have time for one more quick question if anybody has any questions. And if we don't have any more questions, please recognize that you can continue to ask questions as you formulate them in the Q&A box and in the chat as well. So I think that is pretty good here, and we can move on to our last speaker. Thank you, Arun, for the really interesting talk. Really appreciate it. And I am going to have to think about this and form my own questions as I go forward as well. So our last speaker is Claire Yang, also from the University of Minnesota. And Claire is actually an undergraduate, and so that is fantastic to have you here. Thanks for being with us.
Thank you.
And Claire is going to be talking to us today about representing altruism in multi-agent theory of minds, and I am expecting to be blown away here. So please take it away.
Well, I hope so. Here, let me share my screen.
Looks good. Okay, yeah. Whenever you are ready, stage is yours.
Yeah, so this is my first time publicly presenting any research work, so I'm very excited and thankful to Neuromatch for this opportunity. So today I'm going to be talking about representing altruism in multi-agent theory of minds. As you can see, I guess from Zoom, my name is Claire Yang, and I'm a senior undergraduate at the University of Minnesota, and I'm collaborating with Joseph Blanchard, who is a master's student, he's on the call, at the University of Minnesota, and also Dr. Paul Schrader. So there we go. Quick definition to start off with. Theory of minds is the ability to perceive and understand the motivations, goals, and beliefs of oneself and of other people. So this ability is really important for cooperative behavior between multiple agents because one, it allows agents to anticipate other agents' needs based off of their inferred goals and thus work together. So previous work in multi-agent theory of minds has focused on modeling agents who are assumed to have selfish motivations. However, cooperative behavior is difficult to understand if everyone is acting selfishly. And now more than ever in the world, it's very important to understand and study like unselfish behavior and cooperation. So first, in order to solve this problem, we need a way for agents to be able to think about what others are thinking about to a certain kind of like recursive depth. So following the two works cited at the bottom of the slide, we model the agents in what is called a cognitive hierarchy. So basically, a cognitive hierarchy defines agents at different levels, where agents at different levels will follow different policies and take kind of the lower level agents' actions into account in their policies. So for example, a level 0 agents policy can be to randomly select their actions, right? They just maximize their actions or randomly select them with no regard for any other agent's potential actions. A level 1 agent will anticipate the other agents to be level 0 and choose their actions accordingly. And a level 2 agent will, again, do the same, assume other agents to be level 1 or level 0 and also choose their actions accordingly. So our work extends the idea of composable team hierarchies from Chaum et al.'s paper, Theory of Minds, Understanding Behavior in Groups Through Inverse Planning. So basically, a composable team hierarchy formalizes the idea of a cognitive hierarchy as described in the previous slide, but uses it in multi-agent planning. So basically what that means is in a composable team hierarchy, basically each level agent is assumed to have certain reward structures for different combinations of level 0, level 1, or level 2 agents. And based on these assumptions of the reward structures, you can infer over the hidden relationships. The assumptions, however, that Chaum et al. Made was first that each agent is selfishly motivated, and second, that each agent thinks that the other players are less strategic than themselves. So we hope to kind of break out that first assumption and allow for unselfishly motivated behavior. So our work investigates non-selfishly motivated behavior through a different reward structure in the composable team hierarchy, and also it goes a little bit beyond Chaum et al. And introduces the notion of like a social grouping or a team by combining multiple composable team hierarchies so that we can hopefully study team dynamics. So we implemented our model and ran it in a stag hunt simulation. And if you don't know what a stag hunt scenario is, it's basically a classic game theory problem that has been used to study multi-agent behavior. In this scenario, there are 3 agents. Each of them are hunters who are trying to either catch the stag or the hare. The stag, if it's caught, has a very large reward, whereas the hare has a much smaller reward, and the game will terminate when either of them are caught. As you can see, so on the left, there's a screenshot of what the simulation looks like. The stag will move around to avoid being caught, and so thus it can only be caught if 2 agents cooperate on catching it. And so say if 2 agents do catch it, they'll split the reward and each, in this case, take home 10 points each. And the second addition to the stag hunt scenario that we added in was an action of altruistic declarations. So, right, there's the action space consists of being able to move up, down, left, and right, and also declare your altruism at any time step to any other agent. So this declaration basically signals a willingness to cooperate. And as you can see on the bottom right, so the way that I guess I denoted it is the blue agent is not cooperating or has not declared themselves altruistic to any other agent. And the red one has declared themselves to be altruistic towards purple and blue, and purple to red. So in this example, if blue and red were to catch the stag, and in that time step, purple was still altruistically, I guess, declarative towards red, then purple would also share in the reward of catching the stag because they have declared themselves to be, I don't know, like altruistic and thus supportive, and therefore they also get a reward out of that. So our preliminary results basically show that higher level agents are more likely to declare altruism towards other players, in that an agent's altruistic declarations have a notable effect on the inferred teams and the other players' actions. So I did include these videos. We can go into them later, but basically they just show the 2 different, I guess, like situations, one of which is where all the agents are level 1 agents, so lower level agents, and the second one where all the agents are level 2 agents. So given these preliminary results, we hope to continue first experimenting with the reward structure to see if we can simulate more altruistic behaviors, and also add in a dictator game, which is a different game theory game that allows the agents to actually truly signal whether they're being altruistic, because an altruistic declaration does not actually mean altruistic behavior. And in the future, it would be great to be able to utilize this environment to study kind of perception of cooperation in depressed people versus non-depressed people, to understand and kind of introduce a novel methodology into that line of work. So yeah, here's me and my collaborators' contact information if you'd like to follow up, and thank you very much.
Fabulous. Thank you, Claire. And in lieu of applause, please drop your praise in the chat so that people can see how we appreciated Claire's talk. This was really interesting. Thanks. We have a few minutes for questions, actually, which is nice because these are supposed to be the interactive talks. So please utilize that Q&A box or the chat. And to get us going while we're waiting for a few questions to come in, I have a question which may be very obvious and maybe is the question you get all the time. But it struck me that this other assumption that the Shun et al. Paper from 2019 is making, which is that each agent assumes that the other agents are a level below it, or at least 2 levels below it.
Right.
That strikes me as a very artificial assumption for an agent to make, or maybe I'm just reading, I have too much hope for humanity, I'm not sure. But are there plans, or how do you see that assumption interacts with these declarations of altruism? Would they drastically change if you relaxed that assumption?
That's a good question. I guess I've thought about that a bit, and I don't know that I have a definitive answer, but I think the reason why it's assumed that the other agents are at lower levels than, I guess, the root agent, if that, like I would think that these 2 other players are at a lower, less strategic level than me, are basically to limit the space of possibilities, because it's impossible for you to infer what someone else who is more strategic than you would do, right, in the next time step, or what kind of policy they would follow. But if you assume that you are the most strategic person, then you would basically be able to kind of, I guess, assume their policies and then kind of act accordingly. So I think that's the main limitation of the cognitive hierarchy. And it's something that was studied, I guess, in game theory. And my best guess is that it's so it limits the space of possibilities.
Sure. And this is far from my area of expertise. So, I study metacognition and know about theory of mind, but game theory is a little outside what I do. So
I'm still learning too. So.
But it strikes me that an agent, and Arun, I know you're in the same lab, and so you guys are talking about metacognition and theory of mind. And it struck me that, an agent that has kind of metacognitive abstraction capacity might be able to simulate another agent, or at least like predict another agent that is on its level, using those metacognitive faculties. And so, of course, it wouldn't be that an agent could simulate or predict a more advanced agent or a more strategic agent. But what about those on the same level? Is that just not possible?
That might be a question for Arun, if you'd like to take that.
So it should be able to really, this metacognition process, the way we see it, should be able to generate the pathways in some way. So it's like traversal between high level to lower level, if you see. So by generating those pathways, it should be able to really influence the lower level pathway. That's what I could really think about, if I understood your question appropriately. So there's interaction between these hierarchies, but like the generative process at the top of the hierarchy should really somehow influence this lower level hierarchy part. So it might be the similar part in this multi-agent scenario as well. I'm not sure, but.
Got it.
Cool. Yeah. Please jump in, and other folks too. Like, we've got a couple minutes here. These are meant to be interactive talks. So if you want to jump in and join the fray, we've got some questions coming in as well. And Claire, did you want to follow up on that?
Oh yeah, no, I mean, I think that's a great insight and something I didn't really think about before.
Great. And we can talk about this more later, but in the meantime, we've got a couple of questions who have come in that look like they're for you, Claire. So the first question that came in is from Ben Zarov. And Ben is asking, is it possible to formalize what percentage of action a more strategic agent would not do, assuming there are actions that are explicitly bad?
Okay, let me think about that. So is it possible to have actions, like have a probability? I guess, yeah, I'm having a little bit of trouble understanding that.
Sure. Ben, I handed you a microphone. Do you want to clarify a little bit? Oh, you don't have a microphone here. Oh, darn. Okay.
Oh, no. Okay.
Well, maybe we can think, you want to try via text? Okay. Think about it, clarify, and in the meantime, we'll go to Patrick's question and we'll come back.
Cool.
Okay. So Patrick is asking, in the stag hunt scenario, wouldn't the agent always be incentivized to declare altruism? This is a great question.
Right. So that's something that we were kind of struggling with, where we were like, okay, is this really altruism if they are doing it because they want to share in the reward? And that actually is something that varied with the level of the agents that were in the simulation. And so that's, I guess, that's why I included the videos. So for example, the level 1 agents, they all assume the other agents to be level 0 agents who are taking no one else into consideration. And so these games end really fast. I don't know how clear this is, but you can see that they just kind of go after the stag and they just go for it. And they don't necessarily take time to change their altruism. And unfortunately, I don't really have a graphic representation of this because it was just printed in the terminal. But like the level 2 game right here, let me speed it up. Oh no. But basically, this is all level 2 agents, and they're very relaxed. They just keep on changing their altruism and kind of dilly-dallying because they expect that the other agents are probably level 1 agents. And as a result, you know, level 1 agents will probably think that, you know, the other agents are level 0 agents. And it's kind of like, oh, I think that you might think this, so therefore I'm going to do this, and I'm not going to move towards the stag. And so, yeah, I guess the biggest finding is that the level of the agent really influences the behavior. And I think it is right to kind of continue to investigate whether that's actually altruistic, if we define altruistic behavior as like unselfishly motivated behavior. Did that answer your question, Patrick? Or if you have a follow-up question, that's good too.
I actually do have a follow-up question.
Yeah.
So in the level 1 video that you showed, is the cooperation, like, so you mentioned that catching the stag requires cooperation.
Right.
Is that cooperation just happening essentially randomly because each agent just wants to capture the stag?
Yes, because they're basically very motivated to catch the stag, just because the stag, if they catch it, will give them 10 points, assuming that no one else is sharing their, or only one other person is sharing the reward, and then the hare will give you 5 points. Yeah, okay. So I would say it's just, you know, they're just trying to go for the stag, and I don't think it's necessarily a matter of, oh, I'm trying to cooperate with red or purple if I'm blue. I'm just going to go for the stag and try and corner it and get the reward as a result.
Thank you. This is very interesting.
Yep.
Okay, so we have a follow-up from Ben very quickly before we have to close out the meeting. So I'm just going to read it for the folks on the live stream and the recording. Ben Zarov is saying, I was thinking about your statement that it would be impossible to intuit what a more strategic agent would do, which led me to wonder if it was possible to intuit a set of actions that a more strategic agent would not do. I may be thinking about this wrong.
I guess I'll have to think about that more. Because I guess there's like the set of all possible actions. So if you don't know what a more strategic agent would do, and you assume that that space, or like the set of all possible actions minus the set of actions that an agent could do, the leftover would be like what they couldn't do, then I don't know. I feel like you would have to know one to know the other, but that's just like initial thoughts on that.
Okay. Well, I think with that, we have to close up the room before we get booted out for the next meeting. But I would like to thank again all of our speakers. This was a really fun and engaging session. So thank you, Isabel. Thank you, Arun and Claire, for being here and being part of this. And if you want to continue the conversation, of course, you can always go through find your NeuroMatch matches, or just follow people up through kind of traditional means. So thanks again to all of our speakers, and also to our backend technical host, Siddharth Suresh, for making this run smoothly. And we will see you in the next session. All right. Bye, guys.
Bye. Thank you.
Co-organizers of NeuroMatch. And on the back end, helping out with the technical wizardry, we have Siddharth Suresh. And so he's going to make sure that everything goes okay. Marius, I'll ask you to stop sharing your screen here so that we can get set up for our next speaker, our first speaker. So we have 3 excellent talks for you all today. The first talk is from Shuiying Ren at the University of Pittsburgh. And she will be sharing with us a talk entitled An Application of Wavelet Transforms to Identify the Spatial Scale of Multivariate Activity Patterns in Functional MRI Data. And while she's setting up her screen, I will also just remind the audience that we have a Q&A button at the bottom of the screen, so please feel free to use that to submit your questions while Shuiying is giving us her presentation. And you can also feel free to drop stuff in the chat as well. So without any further ado, Shuiying, whenever you are ready, let's go ahead and get started.
Okay.
Looks good.
Hello, everyone. My name is Shuiying Ren, and I'm from University of Pittsburgh. Today, I'm very happy to present our work using the wavelet transform to identify the spatial scale of multivariate activity patterns in fMRI data. So we all know that from individual neurons to larger functional brain regions, the brain is hierarchically organized on different spatial scales. So the brain region that we were interested in is occipital-temporal lobe, which is a very important brain area for visual features processing and object recognition. However, the question of whether information in this brain region is represented on fine or coarse spatial scales during this visual processing remains debatable. For example, some studies have argued that visual features such as the orientation information is represented at the fine spatial scales. Others have also suggested that visual features decoding in primary visual cortex reflects a large-scale bias. Past studies have used a method to tackle this issue called spatial smoothing, in which they smooth the brain patterns before they do the classification. For example, if they want to study a finer scale, they might use a smaller kernel such as the 4 millimeter. And if they want to study a coarser scale, they probably would use a kernel, say 8 millimeter. However, those spatial scales are not independent with each other. In other words, the information extracted on the scale using the 4 millimeter kernel might be overlapping with the information using the 8 millimeter kernel. So how do we overcome those problems if we want to study the information represented on different spatial scales, which are more strictly defined? So the method we used in our study as a solution to this problem is called the wavelet transform. It is a way of using a localized wavelet or a small wave-like oscillation to decompose the signal into a hierarchically independent spatial scales, and where the coefficients at a particular scale and location represents the response of the signal to the wavelet applied. It has advantages over the traditional Fourier methods for examining the spatial structures. So Fourier analysis depend on the sine and the cosine waves that's stretching out to infinity, which can lead to very poor performance in capturing local features of the signal, such as sharp specks. And then in contrast, the wavelets are extended to a finite range. It is very suitable for studying the local features of the signal. We can see here that there's a small speck in the center of the figure. So those local features can be better captured using those wavelets. So in our study, we used the wavelets to investigate the spatial scale of neural representations for visual categories in occipital and ventrotemporal cortex. Here's the experiment design. So the data was first analyzed in Coutange and Thompson-Shields paper published in 2012 about advantages of fMRI short runs over long runs. And the data made available to us by Thompson-Shields lab. So there were 8 participants, and they completed the fMRI scan as they viewed 4 different categories. We can see from this figure here. The 4 categories are faces, places, and man-made objects, and fruits. So only the data from the 16 short runs were analyzed in our study. So each short run has 36 TRs and has 1 block of each category presented in a random order, and each block has 10 trials. So for more information about this experiment design or about the data of long runs, please refer back to their paper. Okay, so yeah, I like this figure a lot. So here's a demonstration of the wavelet decomposition. So based on the 3D fMRI data volume, we use the wavelets to calculate 5 unique scales that describing the coarseness. So here I'm using the condition of faces and the wavelet coefficients projected onto a 2D surface for 5 different spatial scales. So the first row here is the burn region of occipital, and the second row is VT. So the values in the parentheses indicate the number of coefficients transformed using the wavelet on each scale. So we can see that from this, as the scale gets larger, so the resolution gets coarser. So we have those new spatial dependent features that were generated using the wavelet, and then we pass those features to a XGBoost classifier to classify those 4 different categories, and we repeat it for 5 different spatial scales. And here are some interesting results. So in occipital cortex, we were able to classify those 4 visual categories at coarser spatial scales. And here we can see that at scale number 4 and number 5, which contain the low frequency information. I think those results can be taken as the indication that there are significant differences in the amount of information represented at low frequency scales for those categories, which is sufficient enough to drive the categories classification. However, in VT, we were unable to classify categories at any spatial scales based on those new features. And the significance of the results were validated using the 10,000 times permutation test. Okay, so hopefully I'm not overwhelming you with this a lot of information. So to sum up, what is the take-home message here? So based on the results, we can say that the amount of information do differ between the spatial scales, and is largely differentiable at larger spatial scales for different categories in occipital cortex. I think the main virtue of this wavelet method is that it not only can define the fine versus coarse spatial scales more stringently, which is very suitable for any spatial scale dependent analysis, but also it can look at the neural representations differences based on new measurement. Also, I think this study is one of the few attempts of using the wavelets to analyze the fMRI data. So I do believe that further exploration of the wavelets would definitely help us to get more insights and more interesting findings in these neuroimaging studies. Okay, so I guess that's it. So thank you for listening. I'm happy to take any questions you may have.
Fantastic. Thank you, Shuiying. And in lieu of applause, because we can't do that in Zoom, if you enjoyed the talk, please drop some praise in the chat. Very nice. So we have a couple questions that came in from the panelists who unfortunately cannot use the Q&A box because that is how that works. Very quickly, the first question is, what was the train and test data split for your data?
So we use the 16-fold cross validation. So we have 16 runs. So each one will work as the training testing set for the classification.
Great. And then Mohammed, you had a question? You raised your hand?
Yeah, I was writing it, but yeah, I can ask it here also. So from what I understand, the finer scale, of course, has more data points or more features. So could it be that because of that, it's overfitting the classifier as opposed to the lower scale?
Yeah, since due to the time limits, I didn't point it out very specifically. Actually, we use because we for example, from the probabilistic scale, we have more coefficients, right? Actually, instead of using all the coefficients, we calculated the variance of the coefficients, and we call it as the global energy. It's this, we use this kind of feature. We are not throwing in all of the coefficients. We just use the variance of the coefficients. So yeah, so that I think this feature can capture the variability in the brain signals. So that was used for the classification. Does that answer your question, Mahad?
Yeah, it's just that I'm not familiar with this. Analysis. So yeah, I'll have to go around and read about it.
Yeah, I feel like there's definitely still a lot unknown about this method. I think there's more exploration of this method definitely can help us to understand better of this method. Yeah.
We also have another question from Avital Hami in the audience. And so Avital is asking, I wonder if the low spatial scales would represent the anatomical differences between visual categories, different regions selected for different categories.
I think that's a very, very good point. So for our study, I think we are mainly interested in the amount of information represented on different spatial scales. But I think that, yeah, that might be a possible direction for future works, that the lower scales or the finer scales can represent different anatomical differences. Yeah, I think that's a good point. But yeah, since we didn't do the study in that area, so I cannot answer that very, very, very clearly. But I think that's a good direction for future work.
Great, thanks. I have a question actually, because we have a couple minutes left before our next speaker. So one of the things that really struck me, this is kind of a half comment, half question. One of the things that struck me is that the classification accuracy is not necessarily the only thing that's going to change as you change the spatial scale that you're looking at. Of course, there's going to be lots of different things, just the nature of the representation itself. So I wonder if you've thought about extensions of this or next steps that might involve something like representational similarity analysis or other kinds of ways of assessing the nature of the representation, the content of the representation across different regions in a way that speaks also to these different spatial scales.
Yeah, I think those are very, very good points. That yeah, so for like I said, for our study, we only mentioned we were only interested in the occipital cortex or ventral temporal cortex, because these two regions are very critical for visual processing. But I think it would be very interesting to apply this method to other brain areas to study that how neural representations might differ. Also, I mentioned that in our study, we only use try to examine the amount of information represented on different spatial scales. But I think for future work, it might be interesting to examine what kind of information, what exactly represented on different spatial scales, and what exactly the differences embedded in those information on different spatial scales. I think those are very, very good points that could lead to further investigation.
I think especially if you're trying to do cross-modality representational similarity analysis, like between EEG and MRI, that you might find very different answers depending on the spatial scale that you're looking in the fMRI pattern. So I think that would be really interesting to look at. And then we have a quick question also from Mohammed. Do you want to ask it yourself, or do you want me to ask it? Okay, so Mohammed is asking, what kind of wavelet function did you use, and is there a reason for that choice?
I was hoping someone would ask this question actually. Yeah, so the wavelet function that we choose for our study is called complex Diotric complex wavelet transform. So I'm not sure if maybe some of you may be familiar with wavelets, because wavelets have like different like families. So for our studies, we specifically use this Dirichlet complex wavelet transform for two reasons. First is shift invariant. Invariant means that the signals cannot be easily perturbed or disturbed by the motion. For example, I think this is especially good for dealing like neuroimaging data, because sometimes the motion cannot be fully corrected. So this method has these advantages for being signal shift invariant. The second reason for choosing this method is that it's directionality selective. For example, like for 3D volume, fMRI volume, there can be like 28 different orientations isolated to try to like look at the data from different orientations. I think it's very suitable for the 3D data volume. So that's why we chose this Dirichlet complex wavelet transform. Yeah.
Fantastic. Well, thank you, Shuiying, for your great talk and for the fun discussion. Unfortunately, we need to move on now, or fortunately, we need to move on now. So thanks again. And our next speaker is Marius Catalin Jordan from Princeton University. And he is going to tell us, including his shark outfit, about sculpting new visual concepts into the human brain. So whenever you are ready, please take it away.
Thanks, Megan. Thanks, Shuiying. All right, so today I want to talk about how we can model, track, and modify neural representations in the human brain in real time. And the idea is that learning something new requires changing your brain. And that typically occurs through experience, study, or instruction. But today, I'm going to show you a new way of acquiring conceptual knowledge by directly sculpting activity patterns in the human brain. We're going to use fMRI, neurofeedback, machine learning, and a lot of patience. Oh. All right. So we can use neuroimaging to recover information about visual categories from patterns of activity throughout the brain. But it only provides us with correlational insight into how knowledge is organized. So we don't really understand which neural representations are sufficient for you perceiving there's a dog there, or what changes need to happen for you to be able to learn that dogs are a category of things in the world. So after learning to group things into categories, items from the same category become more similar to one another neurally and more different from other categories. So now we hypothesized that we could leverage this exact same process using neurofeedback to come up with a fundamentally new way for humans to acquire conceptual knowledge. That is, if we sculpt patterns of activity in the brain that mirror those that we expect to arise through learning of visual categories, we may lead to enhanced perception of these sort of neurally sculpted categories compared to similar not sculpted categories in the brain. So this is what we're going to try to do today. And we're going to do it using a method called neurofeedback. And this is a non-invasive method. And the basic idea is to show people an explicit measure of how their brain responds to something and encourage them to change that representation in their own brain through trial and error. So suppose our goal is to increase activity in this region. Over you see a puppy. And we're going to tell you, look at the puppy and generate a mental state that will give you a reward. Now, when you're trying to do this mentally, we can measure whether your brain activity goes up, in which case we give you a reward. Here's $1. Otherwise, we give you nothing, or we take away $1, depending on how mean we are. And so over time, we train you to change your own mental representation of something you're looking at without explicitly realizing it. Now, in practice, visual categories respond to complex multivariate patterns over thousands of voxels in the brain, not just activity levels. So we're going to use a similar method, but have participants generate new patterns of activity in their brains, not just up or down regulate them. All right. So we're using neurofeedback to gain this causal access to the building blocks of visual categorization in the brain. And to do that, we took a set of objects that elicited distinguishable neural representations. And this is a cartoon. I'm going to go into what the stimulus set was in a second. And we generated an arbitrary category boundary. And for each point in this space, we're going to use neurofeedback, encourage it to move and create its own separate neural representation category away from that boundary. Now, the idea is that if this training procedure causes neural representations to separate and group into distinct categories, now I'll show you evidence that they do. And if this separation is causally related to the perceptual decision of which category this stimuli belongs to, then we could see the effects of our manipulation when comparing pre and post-training perceptual measures. Now, ideally, we will create new perceptual categories where none existed before. All right. So there are 4 hurdles that we need to overcome for this technique to allow us causal access to subjective experience. We need to build a complex stimulus set where we can select arbitrary categories. We need to figure out what representation to change in the brain. We need to reliably measure and track the multidimensional neural representations we care about so we can change them. And we need to show the changes that we induce translate into neural and behavioral effects at the other end. All right, so let's start with the stimulus set. We created this parametric space of artificial shapes by adding together multiple Fourier descriptors. And I'm happy to chat more about this procedure during the Q&A, but for our purposes, imagine that you start with a shape that becomes the center of the space, and then you create a 2D surface of shapes that vary parametrically with distance from that center. So any 2 adjacent shapes are very similar, but shapes farther apart are very different. And by choosing a diameter on this circle, we can generate an arbitrary category boundary, which we can then enhance and sculpt in the brain using neurofeedback, such that objects along the train direction are pulled apart neurally and potentially perceptually. All right, so we also verified that each direction in the space is perceived in a similar way using a standard psychology match to category 2 AFC behavioral limit. We generated psychometric curves for categorizing shapes along each direction in the space and verified that people didn't have any biases across any of these directions in the space that we created. All right, so next we have to figure out how this shape is represented in the brain in order to manipulate it. For each person, we ran 2 fMRI scans where we showed them shapes spanning the 2D space. And we were looking for brain regions where the parametric relationship that we observe in how the space is built mathematically and how the space is perceived behaviorally was mirrored also in neural similarity. And now this corresponds to an ideal similarity matrix that looks like this. And it's exactly what the neural data looks like across many brain regions. For example, in LO, which is object information, we have a 0.96 correlation between the ideal matrix and the one that we measure empirically. But since we have a good understanding of where in the brain this type of representation might be causally related to you perceiving something that's out there in the world, we use a searchlight to find all the brain regions in each participant that represent the shape space parametrically. So what we're going to do is we're going to target our neurofeedback actively across all of these regions so that if a particular category boundary is enhanced across all of them simultaneously. And that way, if any of these regions is causally related to perception, we maximize our chances to influence categorical perception after we train people. All right, so next we build a model of the multidimensional landscape of brain representations to nudge our objects towards specific categories or patterns in the space. Now, suppose that we have 2 categories and that they elicit overlapping distributions of neural activity and we measure them with fMRI. This is true for real world categories such as dogs and cats. It's also true for the artificial shapes that we have. So we model each category as a Gaussian distribution whose mean equivariance we can estimate from the same fMRI data that we used to find the parametric shape regions a couple of minutes ago with a searchlight. Now, in this example neural space, for objects that fall within that boundary, that unique distribution of a category, such as the red area for category 1, we have a strong prediction that they'll be perceived as members of that category. And we can use our neural model then to estimate a category boundary in this space. And then our neurofeedback manipulation is to push a point in this space that people haven't seen before, that we want to be perceived strongly as part of category 1, away from that boundary in the correct direction as we defined it in the brain. All right. So in the scanner, we use the shape space itself as a neurofeedback. So during each trial, we select a shape from one side of the category boundary, and we allow it to oscillate in a small neighborhood around that point, mathematical shape space. Now, since the space is parametric, this looks like a smooth motion or oscillation. So this is what the participants saw during training. While we're looking at the shapes, participants are instructed to generate a mental state that's going to make the shape reduce or stop its oscillation. That's it. That's all they have to do in the scan. Unbeknownst to them, the oscillation is tied to the neural representation of the shape. So every couple of seconds, we measure the representation of what they're looking at. We compare the brain model we built before they went in the scanner. And if that representation moves away from the boundary, then the oscillation radius is reduced. So this demo, it's pretty complicated, but it's kind of an example of putting all these pieces together and what happens during a neurofeedback trial that lasts about 8 TRs or 16 seconds. And in this demo, the participant actually makes steady progress towards stopping the shape, which means they generate a category representation that we want. To test this hypothesis that we can change neural representation and influence perception, we put everything together into a 10-day experiment. We built a complex metric space and made sure people perceived it in an unbiased way. We found all the brain regions in that person that represented a space parametrically. We built a model of the space and used it to track and modify representations across 6 days of neurofeedback training. And on the last day, we tested what happened to perception of the shapes. To do this, we had to also develop an efficient computational infrastructure to handle all of this in 2 seconds. That was 9 months of my life. All right. So now let's see what we made our participants see. First, we measured whether our neurofeedback training procedure was successful in changing the way the shapes are grouped in the brain. So we looked at the model luck likelihood ratio, which is a measure of category separation. Now, a positive number on this graph means that we achieved our goal of higher neural separation for the trained direction versus the untrained direction. And we see that for the majority of our participants, our procedure changed the way their brain represents the shapes they were looking at, and we had a relatively strong effect across our entire cohort. Now, we found that we changed the brain. We want to see if this translates into a change of how people perceive the shapes. We did this similarly to the shape space norming. We measured psychometric functions of how the shapes along each line are perceived before and after training. Now, neural change is causally linked to perceptual change. Then we predict that after training, the slope for the untrained direction should stay about the same, but we should see a sharper slope in the trained direction, as people should be able to better categorize things in that direction. And so here we're going to look at the difference between the slopes in trained versus untrained. And again, a positive effect means that we've affected people's behavior. And we saw that in the majority of our participants, we could not only change how the shapes were represented in the brain, but also how they were perceived of participants afterwards. When we look at the brain and behavior changes together, we see that the magnitude of the induced neuroplasticity and the perceptual outcome are correlated. So we have a positive linear relationship between the neural and perceptual change across our cohort. The more we were able to sculpt separate neural categories of shapes in people's brains, the more we're able to change how they categorically perceive those shapes at the end of the experiment. All right, so to put all this together, we built a complex set of visual objects that are perceived and represented in the brain in a continuous fashion. We developed a closed loop system that allows us to track and modify neural representations in the human brain in real time. And we have evidence that this process not only restructured participants' neural processing, but also altered their perception and subjective experience. So our work puts forward a few key advances here. First, we provide causal evidence that distributed patterns of fMRI activity in high-level cortex are sufficient for complex perception. We made people learn to group shapes into categories without teaching them anything explicitly, but by manipulating complex brain activity instead. And crucially, we showed that patterns like this in the brain can not just be reinforced or suppressed, as shown by a lot of prior work, but are radically altered to process and sculpt new novel categories into the brain that did not previously exist there to begin with. And this ability to program new conceptual distinctions into the human brain, which we apply to perception, has broad relevance to other domains, such as decision-making, memory, and motor control, that are all involving changing these kinds of patterns whenever you learn something. Finally, our work provides a new potential avenue for clinical interventions that may help mitigate the effects of disorders that might impact the natural function of the brain, such as agnosias, depressions, or autism, or developing new neurorehabilitation techniques that require fine-grained control over these patterns in the brain. And perhaps we can glimpse the distant possibility of one day maybe programming extensive knowledge or complex concepts into the brain directly, bypassing what we normally think of as experience and instruction. All right, so to end, I want to thank all my collaborators, our funding, and you for your attention. If you want more details, check out our preprint on bioRxiv and send me an email or a DM on Twitter.
Fabulous. Thank you so much, Catalin, for this amazing talk. You know, I love this work, and I've seen you present this before in various versions, and I just think it's fabulous. So we have time for a couple quick questions. First, Mohammed in our panel is asking, couldn't this be that the subjects are just modulating their attention to fit the feedback?
So people are paying, modulating their attention. Well, people have to use potentially attention to particular features of the input to probably do this task, but it's unclear exactly how that would change their neural representation unless the patterns actually separate in the brain. So this is what we measure. So it's possible that attentional modulation, top-down modulation, is a mechanism by which you can achieve this. But by itself, it wouldn't be enough unless that actually causes the patterns to separate, which we measure and enforce and sort of ask people to do. But yeah, it's a good question. It's yeah, paying attention is important to be able to even do this. Yeah.
Awesome. And we have time for one more quick question before we move on. Avital Halmi in the Q&A box is asking, well, first, cool project and costume. Any ideas which brain regions contributed most to the formation of new categories?
This is a great question. And again, we targeted all of them, all those regions that I showed you simultaneously. We know that LO, at least the way we defined our ROIs, plays a big role in this, but every person had usually a frontal patch, prefrontal cortex patch, and also other patches that were variable across people, things like IPS, things like parahippocampal cortex, sometimes STS. And those were weaker in terms of parametric representation, but they existed, and a lot of people had a lot of these different ones. And it's unclear from our data exactly which one contributed the most, but it's a really cool question to start answering in the future, to do targeted neurofeedback with some of these regions and see what can we affect and what we can't affect in terms of neural representation and people's behavior. That would be really cool to do.
Awesome. Well, I have lots of questions, but unfortunately we are out of time. So we'll thank Catalin once again for the fantastic talk, very exciting work, and we will move on to our last speaker of the session. And so for our third talk, Mohammed Abdelhak is going to, from Washington University in St. Louis, is going to tell us about visual misrecognition and how it reveals contradiction between lower and higher visual cortex activations. So take it away.
Hello, everyone. Thank you, Megan. So today I'm going to be talking about when we make mistakes in visual recognition. So usually, this is the time where I should be reviewing the previous literature, but I prefer to just play a game. So I want you to look at this picture as it's changing and see when you would be able to recognize the content of this image. All right. So I'm not going to ask you how did you perform, but you can actually look at how you performed in comparison to AlexNet. So the AlexNet usually would fail at about this 6% blur level. And I actually, when I was starting my PhD, I did this with some of my lab members, and this is their results. So apart from one person, everyone did fairly good performance, much better than the DNN. So basically, when we see those kinds of blurred images, we kind of we don't know what's in there. We might even have some illusion of some other category of the object inside of there. And then we start to correct our recognition as the image gets clearer. So, and this happens due to what's happening in the visual cortex, where we have a hierarchical processing that is happening in the lower visual cortex, and then the information gets passed on to higher visual areas like the LOC and FFA and PPA. So these are they are responding to complex shapes like objects or faces or scenes. At the same time, there's also a top-down pathway where the brain is trying to correct that. So like if there's something that is not is not very clear, so what happens is that the brain is trying to actually improve those representations. So what we did before in a previous study is that we were showing blurred images, and then we were trying to see the effect of top-down modulation and whether there would be an effect would be a difference in this top-down effect between the images that were recognized correctly versus the ones that were not recognized correctly. And we actually did not find a significant difference. So yeah, the experiment I'm gonna explain. So, and also the details of this study is available, already published in 2018. So, but the point is that when we didn't find this difference, I thought like, okay, so how is actually misrecognition represented? So we ran a very similar experiment to the game that you are just playing now. So inside of fMRI scanner, we had 5 subjects, and they would, they would see an image that is highly blurred. So that one is the highest level of blurring. And then when the fixation changes, then the blurring level starts decreasing. And then we have 4 levels of that. And inside of the scanner as well, for each of those images, the subject says they have 5 categories that they choose from. And they have to tell us which category that they are seeing and for each image. So as the blurring decreases, they also can change their recognition strategy as well. And then we have different images that start to appear. So instead of going through the normal way of having an MVPA classifier, we decided to go something a little bit more complex in order to avoid all of the problems with the MVPA where you have repetition suppression. So instead, we trained a classifier that instead of decoding the category, it decodes the DNN features. So basically, separate from this experiment, there's another experiment where the subjects see a lot of images, and then the same images are fed into a DNN, and then we try to predict the different features from different layers of the DNN using a sparse linear regression model. And then we run our blurred images into this classifier, and then we have a decoded DNN features. So those decoded DNN features, first thing, we start to see how similar they are to the features that come from the actual image, like the very sharp one, and see how much they are correlated to see if there would be a difference in those correlations between the actual images and the incorrectly recognized ones. And at the same time, we also train a decoder to predict the category probabilities of all of our 5 categories. So that is only trained using the DNN features. So because we only had a very small number of amount of data, so if we use just DNN features, then we are not tied. And then we also have the behavioral response that the subject says. So we do a one-hot encoding to get probability values from that behavioral response and from the true category as well. So we had a very small subset of points where the subject actually had made a mistake. These are the ones that are showed in the darker gray here. And then we started seeing the correlation between the difference in correlation between the correct and incorrect. And we did not find any significant difference in either the lower visual area, so that's V1, V2, V3, or V4, which is intermediate, but we found a significant difference in the higher visual cortex for that correlation. And then at the same time, we started looking at the behavioral difference. So we started to get the output of the category probabilities as well. And whether are those category probabilities, do they represent the true category or do they represent the behavioral category? And what we found in that LVC did not show much of a difference, generally because LVC has a very just spatial patterns rather than actual representations of categories. But at the same time, we found that V4 actually favored the true category, even if the subject has misrecognized the image. So those results on the right are for incorrectly recognized images, while the HVC saw the opposite. They saw the behaviorally recognized image or the incorrect category. So we found that this is really fascinating, that in the previous, earlier areas, the brain is seeing the actual category, but that then reverses in the higher visual areas. So then we started to see, okay, so would those higher visual areas correct themselves as the subjects correct themselves? Oh, sorry. Yeah, so this is just a sample of the categories. And here on the right, that's actually the category difference. So you can see that consistently HVC is lower. So that's computing the Breyer score, which is a score for similarity and probabilities. So lower is better. And V4 is the opposite pattern. Yeah, so then we saw, okay, so the subjects can do those reversals. They can see the image actually, they first would make a mistake. Of course, not all of the subsequences, they make a mistake. So we pick only the ones where they make mistakes, and then they start correcting themselves as the image gets corrected. And then we start to see whether the representations would persist for the wrong one, or would they correct themselves, and what happens in different visual areas. And the interesting part, we see it here on the right, LVC doesn't show a lot of difference. So here, this is a measure of the true versus the incorrect one. So more red means it's more biased toward the incorrect, and blue more towards the correct. And we can see the HVC is really interesting, where you can see this gradual change where it goes from incorrect and then it starts to correct itself very gradually. Problem with this is that here we don't know where the reversal points are, because sometimes the subjects change after the 25%, sometimes they change after the 12%. So we went through to take one before and one after. And we can see here also the before, the Breyer score difference, or the mean squared error, is lower for the true category, while in the HVC, it starts to differentiate as after this reversal. And we also, if we look at the ones on the right, then we can expect that this actually gets stronger as the image gets more clearer. Yeah, so in conclusion, we can say that the lower and intermediate visual areas do not seem to be affected by the misrecognition. And on the other hand, the higher visual cortex does appear to account for those behavioral responses elicited by the subject. So we can actually check or find that the visual insight is happening in those higher visual areas. And they have been shown, but only on the signal change, or the signal strength in the percent univariate change. So this is the first one we show this pattern differences as those reversed. And it would be interesting to see more results from different image degradation techniques. So I'm currently looking at data that comes from Mooney images and also gray blurred images as well. So if we find like something that is we can generalize to different degradations, I think we can find like a more general pattern or general mechanism that happens inside of the brain. Yeah, so in the end, I'd like to thank all of the members that helped me with this study in Kyoto University and the ATR in Japan, and also Kokoro no Mirai Center, which is the fMRI scanner staff that help, and of course, all of the funding bodies. Thank you.
Fantastic, thank you. And again, in lieu of applause, because we can't do that in Zoom, if you enjoyed the talk, please drop some praise in the chat. But this was also a great talk. All three of these were just fantastic. Thank you all so much. So while we're waiting for questions, we have a few minutes here where we can do questions. I have maybe a silly question, which is, Catalin, did you have a question? Did you want to ask?
You can go ahead. Yeah,
okay.
You can go ahead first.
So my silly question is, you would never expect to see something like this in a purely feed-forward network like AlexNet, right? And so if you did exactly the same analysis, you would not see this effect, or would you see higher choice probabilities in the later layer?
Possible, actually. I think because sometimes the lower visual areas are more similar to the actual one, but then it starts to change after that, because what kind of patterns it tries, it ends up looking or finding to be interesting. So it's possible still to happen in a feed-forward network. However, I'm interested to look at also if there is something that is coming from more deeper areas that tells the subject, are you getting that from some memory? And I did find some indication, but it's not exactly that strong. So yeah, if I include that, the reviewers will jump at me.
Sure. Yeah, I was just wondering how much we can, or what kinds of future work we would need to do to really differentiate between kind of just a pure kind of evolution of choice probability as you go forward in a feed-forward network versus like these true top-down influences that we're talking about here.
Yeah, I'm currently trying to look at something that is even more deeper, so more of a modal. But the problem with that is that they have like some of those areas don't work except when you're misrecognizing the image. So using a decoding approach would be hard because you cannot actually train the decoder, because when you're training with clear images, those areas don't work at all or don't contribute. So they just don't get trained.
Right. Okay. I'll cede the stage here to Catalin. Did you have a question?
It was actually quite related to this discussion. I was thinking, so for the Mooney images, it's like you get an effect, you immediately can tell, whereas for these, there is a more clear effect of maybe potential gradual accumulation of evidence. I was wondering if you have different predictions as, I could see how it could be a similar effect here, technically, even for Mooney images, still with the same stimulus has been accumulating evidence, at some point it flips. But I was wondering if you expect to be able to even to tell these kinds of effects with this method.
Yeah, I actually, for the Mooney images, what I did is that I blur the image first, and then I do Mooney like thresholding. So in this way, we can actually have different levels of Mooney, one with more smoother edges and one with much more detailed. So the much more detailed would be easier in general to recognize, especially if we have only one object in the image without much clutter around it. So in some cases, yeah, Mooney images do get recognized.
Okay, we have time for one very quick question before this room closes up. So Avital Hahami is asking, so would you say that based on your findings, early visual cortex is irrelevant for conscious perception, ... And I think this is a great place to end the session.
Yeah, that's a very good question. So I would not go that bold to make that claim, because I would say that it's early visual cortices still get modulated from using a top-down modulation. Actually, our previous study was focused on that. But the point we're trying to raise here is that it doesn't get to the extent that you are changing categories. And it could be that our subjects are just, I don't know, so I'll just pick a random category.
Yeah. This is kind of a question about whether, the posterior hot zone or top-down influences and higher order, influences on phenomenology are the right way to go. And we could debate this all day, I'm sure. But unfortunately, we don't have time to do that. So I'd like to thank all of our speakers once again. This was a really fun session. So thanks for being here. And thanks also, of course, to Siddharth Suresh for tending to the back-end technology needs. And we have one more parallel session before NeuroMatch ends. And then we also have a closing, session as well. So I encourage you to come to that if you are still awake or wherever you are in the world. And we'll also have, I think there's a Halloween costume competition that will be announced at that point. So hopefully we'll see you there. And thanks again for this great session, guys. This was really fun. So we'll see you next time. Bye.
Thank you, Megan. Bye.